Okay, good morning, everyone. I hope you can hear me. Welcome to the third Top and Electroweak session of the week. This session will be dedicated to highlight rare top TT bar and single top associated production. And it will be followed by photon-photon physics results, and later on vector-boson fusion and scattering. And we are going to start with the top-related talks. I will remind you, remind the speakers when 5 minutes of time is left for their talks. And I would also like to advertise that we will be having a discussion session right after this session, so around 12:55 or so, dedicated to photon-photon processes. And also the poster session will start shortly after, so be sure to stay connected to attend all these great results. All right, so let's go ahead and start with the first talk of today by Nedaa, who is going to tell us about four-top production results from the ATLAS experiment. Nedaa, are you there?
Right. Yes, can you hear me?
Yes, very well.
All right, I'll share my screen then.
Yes, that would be great.
All right, can you confirm that you see my slides?
Yes, we can see your slides. Please go ahead.
All right, so I'm happy to present to you the measurement of four-top quarks on behalf of the ATLAS collaboration. Just to remind you, we're looking here at a process with a very complicated one. At leading order, we expect 72 gluon and 12 QQ bar initiated diagrams. And here you can see two examples of the leading order one as well as the sub-leading order as well diagram. So despite the fact that this is an interesting process which hasn't been measured yet, it's also sensitive to top Yukawa coupling. A non-standard model value of the Yukawa coupling can change dramatically the production via an off-shell Higgs, as well as through this process at extremely high energy scale production, it makes it naturally sensitive to many beyond standard model scenarios. And here we have listed a few of them, such as EFTs, including four fermion contact interaction, or through Higgs physics, as well as scenarios from SUSY and any potential new particle that could couple to the top quark. And also here, just to give you an remind you of the rare process that we're looking at, that it has a very small cross-section compared to, for example, TT bar, which has several of hundreds of picobar, and the four-top has a cross-section at next to leading order in QCD and QED at 13 TeV of 11.97 femtobar. As in terms of events, we would expect something about 100 million events of TT bar, whereas only 1,000 of four-top events. And we know that the top decays into a W and a B, which means in the detector signature is defined by a presence of several up to 4B quarks. And of course, then the decays of the W, which can decay leptonically or hadronically, resulting in the different final states that are depicted in the pie chart here. In terms of the analysis, we split them into two different channels. The first one that covers the 1 lepton and 2 lepton opposite sign, which together gives the largest branching fraction. However, this channel has a large irreducible background coming from tt+jets, mainly tt+ heavy flavor jets. And this will be the first analysis that we'll talk about that covers 36 inverse femtobarn of run 2 dataset. Then we have the other channel, the 2 lepton same sign, and at least 3 lepton. So together they have a low branching fraction. However, they have small background coming from TTW, TTZ, non-prompt leptons, charge misidentification. And this is the most sensitive channel, and that's the new result that we will highlight in this talk that uses the full run-2 data set of 139 inverse femtobarn. Starting with the 1L, 2L opposite sign channel, as I said, this used only a partial data set of run-2, which is 36 inverse femtobarn. We require 1 electron or a muon, or exactly equal to 2 electrons or a muon. In the 1 lepton channel, we request at least 5 jets. In the dilepton, at least 4 jets, and in both channels, at least 2 tags. However, in the 1 lepton channel, we expect 4 jets and 4b jets in our signal region. In the opposite sign channel, we expect 8 jets and 4 of those to be b tags. As well as we impose other cuts on the missing ET, the MTW, in the 1 lepton channel, in the opposite sign on the invariant mass of the 2 leptons, in order to suppress a background such as the ones coming from multi-jet, non-prompt leptons, and so on. So we have then categorized our events according to number of jets, which is here shown in this diagram on the x-axis, on the number of b tags, which is on the y-axis, and then as well as the reclustered large jets with a radius of 1. Then we form different regions as the efficiency extraction regions, source regions, validation, and signal regions. And this is here an example from the single lepton channel. Then for the background coming from tt+jet, which is, or mainly the one coming from ttbb, is estimated using data-driven method, where we extract efficiencies in the low end jet regions, that's here in purple. And then we apply it and parameterize this efficiency as function of the PT of the jets and the delta R of the jets in the low source regions, and in order to promote the events in the higher regions, in the signal regions. And as well, we have a validation region in order to validate the data-driven method that we follow in order to estimate the main background coming from tt+jets. And then here we have the example from the single lepton channel in the 9-jet and at least 10-jet region, showing the data Monte Carlo agreement post-fit. On the left, the 3B regions, and on the right, the 4B regions. You can see the background from tt+jet, which is from data-driven estimate, is in white, and then we have other backgrounds coming from TTH, TTV in green, and non-TT bar ones are very tiny, and they are in yellow in the plots, as well as the four-top signal is in solid red. So this is here the HT hat distribution, which is basically the scalar sum of the PT of the jets. And a simultaneous fit has been done in the multiple signal regions. We have here a total of 20, which is a sum of 12 regions in the single lepton and 8 regions in the dilepton channel. With this fit, we had no significant excess of events above the standard model background prediction, excluding the standard model four-top prediction is found. In case of a four-top production with standard model kinematics, and observed expected 95% confidence upper limit on the production cross-section was found to be 47 femtobarn, 33 femtobarn expected, and this corresponds to an upper limit on the cross-section relative to standard model prediction of 5.1 observed and 3.6 expected. Then the signal strength mu, which is basically the measured cross-section divided by the theoretical cross-section of four tops, was found in the combination of both the single lepton and the dilepton channel to be 1.7 plus 1.9 minus 1.7. As you can see here, the breakdown of the stat and the systematic uncertainty, that this channel is dominated by the systematic uncertainties, and mainly from the ones coming from the TT bar modeling. However, this was, of course, with the small part of the run-2 dataset, and stay tuned for the updated results using the full run-2 dataset. And now we move to the second channel, which is the new result from ATLAS that uses the full run-2 dataset of 139 inverse femtobarn. And in this channel, we target clean leptonic signatures where at least 2 of the W bosons decay leptonically. So we require 2 same sign leptons or 3 leptons. And here we mean by lepton an electron or a muon. We request at least 6 jets and a PT above 25 GeV. 2 of the jets to be B-tagged using the 77% efficiency working point. And then an HT above 500 GeV. And here it's HT all, which basically scalar sum of the PT for both the leptons and the jets. After such a selection, we're left with different sources of backgrounds, which are here shown in the pie chart. So let's go through these several types of the background. The first category, we refer to it as the reducible backgrounds, which is coming from fake non-prompt leptons and charge misidentified leptons. And those are the ones here that are in the black box. So for fake and non-prompt backgrounds, they are mainly coming from electrons or muons from heavy flavor decay. Those are the ones in purple. Electrons from photon conversion in the detector or atelier conversion, which is about 6.8%, and a virtual photon leading to a plus E minus pair. And this is shown in the darker purple color. We also then have background coming from charge misassignment, which is specifically relevant to the 2 lepton same sign channel, where we have a charge of an electron is mismeasured due to either Bremner-Strelong photon emission followed by its conversion, or mismeasured attract curvature. And this is in the light green, about 5.8%. Then we also have irreducible backgrounds, leptons from WZ or leptonic tau decays, mainly coming from TTW, which is in the light gray, about 36.7%. That's the largest one, as you can see from the pie chart. Then we have TTZ and TTH, processes with same sign and multi-lepton plus jet signature, basically with additional light and B-tagged jets. Then we also have some other smaller backgrounds. They're combined into the 10% you see in the green, which are others, such as diboson, triboson, and so on. And then we also have a small contribution from 3-tops, which is in the light blue color. These backgrounds are evaluated using Monte Carlo, normalized to standard model cross-section, except for the TTW, which is floating in the fit. And now we come to the part of how do we estimate these backgrounds. We have a template method. It's used to determine the major backgrounds, where we have the shapes of the several backgrounds is estimated from Monte Carlo, and then normalization is obtained from the fit. So we have defined in the analysis several regions where we have dedicated control regions that are defined in order to constrain the normalization factor, and the modeling is, of course, validated in validation regions. So we have defined 4 control regions that are dominating component or a variable with a discriminating power between the several components. We have a region for TTW, a region for the heavy flavor electron or muon, material conversion, and low MEE. As you can see here in the table, there are different selections on the flavor of the leptons, number of jets, number of B tags, in order to determine a region that is dominated with a specific background. And we have one signal region. So the analysis has a total of 5 regions. Then from the template fit, we obtain normalization factors, and they are here listed for each of the main backgrounds. As you can see from these factors, they're compatible with unity, except for the factor of TTW, which is 1.6 plus minus 0.3, and also as well the factor for material conversion. However, this is not surprising, the high factor that we get for TTW. It's compatible with a previous similar analysis with a similar final state, the TTH H2 multilepton results. So it's not surprising, but compatible. We also then looked more into the TTW, and we have defined a specific validation region where we require at least 4 jets and at least 2 be tagged, and this is the TTW validation region. This is here the number of jets. The TTW is in the gray, and the data are in the black points, and then other backgrounds are in green.
Sorry, Nedaa, you have about 4 minutes.
Okay. And here we see that we have a good data Monte Carlo agreement up to 6 jets, whereas we have an overshoot in the 7 and at least 8 jets. So we have assigned an additional uncertainty of 125% for exclusive 7 jet and 300% for at least 8 jets. And this is basically based on the validation region mismodeling that we see here. And then we also assigned an uncertainty of 50% to events with 3 or at least 4 B jets. And this is based on ttgamma data Monte Carlo agreement. Then after determining the background, we in the signal region, we use multivariate techniques based on the boosted decision trees. We have 12 observables that were selected that show a good discrimination power as well as a good data Monte Carlo agreement. Here we have 2 examples, the sum of the B-tag score and the minimum delta R between the two leptons. And then we feed all these 12 observable, and we get a BDT score, which is the observable that we fit in the signal region. The BDT is trained inclusively in lepton flavor and multiplicity for the events in the signal region. And this is here we see the post-fit data Monte Carlo agreement, and very nice agreement between the data and the BDT in the high tail and the signal four-top in solid red. So we also have several sources of systematic uncertainties, and this is here the breakdown on the signal strength. So we have, of course, the statistics in this channel is important, and then we have on the modeling side the modeling of TTW has a large contribution. And then we move to the results. So the four-top production cross-section is measured via a bend likelihood fit in the of the BDT score distribution in the signal region, and the discriminating variables in the 4 other control regions. We measured a signal strength of 2 plus 0.8 minus 0.6. With this result, the cross-section determined to be 24 plus 7 minus 6 femtobarn. And this is compared to the theoretical cross-section of 12 plus minus 2 femtobarn. We have a strong 4.3 sigma, 2.4 sigma expected evidence. This result is consistent with 1.7 sigma with the standard model. And we have done several tests in order to check, of course, the stability and consistency of the result. And here I leave you with an event display of a four-top candidate event. So we have same sign electron in green, muon in red, 7 jets in the yellow, 4 B jets in blue, and an HT of 723 GeV. And stay tuned for the full run-2 data combination. Thank you.
Thanks a lot, Nedaa, for this very nice talk, and congratulations on this evidence for four-top production. I'm sure there are questions, so please don't be shy. Raise your hand so that I can see. Okay, so if no one dares yet, can you go back to the systematics table?
Mm-hmm.
Can you explain a bit? Are these normalization or shape uncertainties, which are the ones, so what contributes more, normalization? What is the impact of any shape uncertainty?
So this is here the combination. So it's the final effect of each of the uncertainty. So it's a shape and normalization.
Okay.
So is there any specific one that, for example, is it for the TTW?
Exactly, I was wondering about that one, yes.
Yeah, I'm not 100% sure if it was more a normalization or a shape. It could be, I think it's a normalization.
Yeah,
because
okay.
we have a very high normalization factor as we saw from the temperature.
Exactly.
Yeah.
Okay, thanks.
Also a large impact of the uncertainties on 7 jets and 8 jets, of course, which is huge. I don't know, yeah, perhaps it's a shape uncertainty in the end, because we feed BDT and this uncertainty is applied to events with additional 7 and 8 jets that enter BDT. So of course it changes the shape of the BDT. The same if you change, there is uncertainty on the heavy flavor content of TTW. Again, it enters BDT and it changes the shape. Since we fit basically in the end to extract the signal only one distribution, all these uncertainties also affect the shape of this distribution. And there is a dedicated Monte Carlo based TTW uncertainty comparing different simulations. That's a different, an extra one. Not to mention what Nedaa said, overall normalization factor.
Okay, thanks a lot.
There is a lot.
Yeah, sure. Thanks a lot. Thomas has a question. Go ahead.
Hi, Thomas Giro speaking. Looking at the same table, I noticed that the dominant uncertainty is the tt cross-section. Can you say a little bit more about that? Is this basically due to scale and PDF variations, or?
So the one that is the cross-section is the uncertainty on the theoretical cross-section that we use. And the modeling is from basically PDF and changing of the shower of the generator.
Right, I think theory uncertainty, well, it's a calculated one, so it's out of our hands, it's in your hands. It was scale variations. Okay. I don't think we evaluated PDF because scale variations were already giving us 20% about, so perhaps PDF is not a large effect. And of course, it enters only mu calculation in the denominator.
Mm-hmm. Okay, thank you.
Any more questions or comments?
Yeah, one small observation on what Thomas was asking. So,
go ahead.
And Lisa also pointed out, it enters the mu calculation. We are measuring, quote unquote, we're trying to measure, of course, we don't have observation, but we're trying to measure for tops. So if you, for a moment, abstract from what we're discussing and come from far away in the universe, you say, hold on, you're measuring 4 tops and you have an uncertainty on the 4-top cross-section. What are you talking about? This is the mu. It's the comparison between what's observed and what is the theoretical calculation. But I mean, if you want to talk about the experimental aspect, the relevant uncertainties are the other ones. So it's TTW plus jets. That's the dominant effect. If we're talking about cross-section, take that standard model theoretical assessment out and in your mind and refactor these uncertainties in that feature. And the message from the table is that we are dominated by the fact that we do not understand TTW plus jets at the appropriate level.
Okay, thank you.
Okay, thanks a lot. I think we need to move on. So thanks a lot, Nedaa, again.
Thank you.
And now we move on to Andrea, who is going to tell us about TT bar plus jets, 4-top and B bar from the CMS side.
Okay, thank you very much. Good morning, everybody. On behalf of the CMS collaboration, I'm presenting the latest results on top quark pair production with 2 additional generic jets, or 2 B jets, or 2 additional top quarks. Okay, so why we want to measure TT production plus something else? Well, because of the large mass of the top quark and the large Yukawa coupling, top quark physicalize the boundaries of standard model territory. So we want to map this area as fully as possible. So not only the production of pairs, total or differential cross-section, but also the production of something else in addition to pairs. For essentially 2 reasons, because TT plus something else events are important as backgrounds for rare standard model processes, but also because they might be related to new physics beyond the standard model. And in this case, TT plus something else production can also be interpreted using the effective field theory modeling. Specifically, tt+jets, tt+bb are indeed important backgrounds for TTH production and for events beyond standard model. That's why we want to improve the simulation by recurring to precise measurements. And in terms of next to leading order calculation, they are affected by large uncertainties associated to renormalization and factorization scale. And in that case, they are referring to 2 possible scales, the mass of the top and its victim. In addition, there are different energy scales associated to generic jets or to the B jets. And regarding B jets, there are also different possible approaches considering massless quarks or massive quarks. So those are the reasons why it's important to cover this area. And regarding 4-top events, we heard a few minutes ago that there is good evidence from Atlas, but it's not full evidence for an observation. And that is because the cross-section is very, very small. The good thing about 4-top events is that they allow a constraint of the topics Yukawa coupling, but also they are very sensitive to the possibility of new physics beyond the standard model. For instance, the 2x doublet model, supersymmetry, and so on, as you heard a few minutes ago. Having said that, let's move to the results. I will discuss here the most recent results of 13TV, namely tt+jets, tt+bb in the single lepton and the lepton channels, tt+bb in the all-hadronic channel, 4-top production in the single lepton and opposite sign dilepton channels, and 4-top production in the same sign dilepton and trilepton channels. And only for this last case, I will be referring to the full integrated luminosity of Rancho. Now, let's begin with tt+jj, tt+bb in the lepton plus the lepton channel. Of course, the selection refers to number of leptons, number of jets, and number of beta jets. But what is important here is to determine the origin of the additional jets. So in the dilepton case, there are few jets around. So additional jets are considered as those which have the third and fourth highest score for the B-tag indiscriminant. While in the single lepton case, there are more jets around, so there are more possibilities and permutation. So before picking up the additional jets, we apply a top anti-top kinematical fit, and the jets which are not chosen in the fit are those which are considered as additional jets. Now, again, the important thing here is the important quantity here is the B-tag indiscriminant of the two additional jets. And you see here in the plot what is the comparison between data and all the possible yields for the dilepton and single lepton channel in terms of these two discriminants. There is a good consistency with respect to the sample composition. The analysis is carried in two different phase spaces. One is a visible phase space, which is essentially matching the number of particle level lepton and jets defined in the selection. And then there is a full phase space, which refers to all decays, but considering at least two generic jets or two additional B jets. The fit to extract the parameter of interest is a maximum likely beam fit in the visible phase space to the two-dimensional B-tag indiscriminants, which are shown on the plot. And the parameters which are obtained are the cross-section for top-top jet-jet, generic jets, and the ratio between the cross-section for top-top and two B jets and top-top and two generic jets. And these fits are carried independently in the two channels because the two channels have a different phase space and different background. And from the visible phase space, the results are then extrapolated to full phase space, accounting for Monte Carlo acceptances. So here are the results. In the visible phase space, the cross-section for top-top jet-jet has been measured, as shown on the plot, and it's the measured value is quite close to the standard model expectation, while for the ratio, the observation is about 30% higher than the standard model expectation. And the most sensitive channel is the lepton channel, and in this case there is a 3 sigma significance, which improved with respect to a previous result. Now, in terms of full phase space, please look at the plot on the right. Again, top-top jet-jet cross-section has been measured quite consistent with all possible kind of generator, while the ratio again shows about 30% value larger than what expected from Monte Carlo. Now let's move to tt+bb in the all-hadronic channel, and this is the first measurement here in this channel. The selection again requires a nominal number of jets, out of which at least 4 must be B-tagged, and those 4 jets include the 2 additional B jets. But then to suppress the backgrounds and to better identify the jets, we need to require to something else. And indeed, we require to 3 multivariate discriminator. One is based on a quark-gluon likelihood, and this is favoring events associated to 4 quarks rather than events associated to 4 gluons. Then there is also an additional boosted decision tree needed to reduce the multi-jet background. And in order to better pick the jet permutation, there is again a boosted decision tree based on dijet and trijet invariant masses. On the plot, you see the first discriminator, the quark-gluon likelihood, and the third discriminator called the classification without labels. And those are the distribution chosen for the final selection, which requires the first one larger than 0.8 and the second one larger than 0.5. Anyway, the consistency of the distribution with the sample composition is good over the whole range of these two discriminants. Also, in this case, there are two fiducial space definitions. One which is called parton-based, PB, and refers to partons after radiation, and one which is called parton-independent and refers to stable particles after ionization. After that, the total phase space is obtained from parton-based phase space after accounting for acceptance correction. The analysis refers to a two-dimensional B-tagging discriminator, considering the largest and next to largest discriminator scores associated to the additional jet chosen according to the permutation BDT that I described earlier. And then these two-dimensional plots are considered in 4 different analysis regions. One, which is the signal region, shown on the upper left, and then 3 control regions in the other panels. And the two-dimensional discriminator is enrolled to 1 dimension just for clarity in this plot. Again, good agreement in all bins of these discriminators. And here are the results. The cross sections are obtained from a fit with a profile with maximum likely technique to the two-dimensional B-tagging scores in the 4 data regions. And the table gives the results in the parton-independent phase space, parton-based phase space, and total phase space. And the measurements are compared with with different generators. And also in this case, we see that there is an overestimate of the measurement that we expect to the expectation by a factor 1.5, 2.5. Anyway, the cross-section measure in this case is of 5.5 picobarn with about 1.6 uncertainty. The plot on the right shows a comparison of the cross-section in the 3 phase spaces with respect to different choices for the generator. It's consistent within uncertainty, but there is again an overestimate with respect to the expectation. Now we move to the production of 4-top-quarks. Also at CMS, we have 2 different channels, and the first one I will describe is single lepton plus opposite sign dilepton. Again, the selection refers to a number of leptons and jet.
Sorry, Andrea, you have 5 minutes.
Sorry? 5 minutes.
5 minutes.
Yes. To a number of lepton and jets matching the channel request. In this case, you see on the plots how well the data match the sample composition in terms of this specific quantity number of jets, but similar plots are available for different kinematical quantities. Of course, the expectation from 4-tops is very small. In order to identify the top quarks and to improve this very small signal-background ratio, we apply boosted decision trees trained separately in the 2 channels, so one for single lepton, one for the lepton, and then for increasing the sensitivity, the events are categorized based on the number of jets and number of b-jets. In this case, you see one example of these templates for single lepton or dilepton for a given choice of jet multiplicity, but also for different choices, and no significant deviations are observed for all the discriminant distributions. So these distributions are used for obtaining a signal strength defined as a fraction, as a ratio between the observed cross-section and the expected cross-section, so the maximum likely fit. And the table gives these values of the signal strength and also the significance of the value. Of course, these significance in this case are very small, so we need to refer to upper limits, and the upper limit on four-top production would be of the observed upper limit would be of 48 femtobar at 95% confidence level. Finally, let's move to the second channel for four tops, same sign dilepton and trilepton. Again, the baseline selection is based on lepton and jet multiplicity plus some additional kinematic request. And the main backgrounds are from TTW, TTZ, and TTH. Production, in this case, simulation are corrected to fix some observed visual Monte Carlo discrepancies. Next important background is non-prompt lepton background, which is obtained from with a database method. On the plot, you see the comparison of the data with the predicted yields in terms of all the relevant quantities used in the selection. There are two analyses, one which is called cut-based, 14 signal regions and 2 control regions defined in terms of multiplicities, jet and leptons, and the second one which requires a BDT using the same quantity plus some additional kinematic variables, 17 signal regions and 1 control region. Of course, the second analysis is more sensitive and precise and will be the one used for interpretation. In the plot, you see for the BDT analysis a comparison of data we expected to yields, predicted yields for all those analysis regions. But a similar plot is available for cut-based analysis. Here are the results for the cross-section. The cross-section for both analyses amount to about 10, 12 femtobar with large uncertainties. So the significance either observed or expected is below 3 sigma. That's why we introduce upper limits of about 20 femtobar for the observed limit and of about 9 femtobar for the expected limit. Comparing the cross-section, considering the dependence on the standard model cross-section on the Yukawa coupling, we can also extract a constraint on the Yukawa coupling, which is smaller than 1.7 times the standard model value at 95% confidence level. Finally, four-top events can be considered as background for more exotic events, like in this case, the production of a scalar or a pseudo-scalar for the 2x doublet model. And in this case, we set lower limit on the mass of the scalar of about 470 GeV, a lower limit on the mass of the pseudo-scalar of about 450 GeV. Okay, I'm ready to conclude. CMS has measured the production of top quark pairs along with 2 generic jets, and the cross-section is measured as expected, and together with 2 B jets, and in this case, the cross-section turns out to be about 30% higher than expected. So in order to better understand this case, we need to increase the precision on ttB production, including the latest measurement, and try to reduce the effect of statistical and systematic uncertainty. as for four-top production, you are getting close to observe four-top production, but the significance is still small. Thank you.
Thank you very much, Andrea. Questions to Andrea?
Hello, Andrea. This is Francesco speaking. Do you hear me?
Yes.
Ciao. So I have some questions on the very interesting tt+jets measurements that you have, the lepton, dilepton, and holodronic.
Yes.
One is more specific on the analysis, and another one is more general. So the one on the analysis, more to understand, because I really like the idea of measuring everything together, and I think it's a very powerful approach you've chosen here with the dilepton and single lepton. So how is the ttjj and ttbb, ttbj, ttcc, ttlf? You have all these categories. How are these templates determined? Is it ghost matching? And is the BB and BJ category defined? Are they defined differently? How do you separate between these?
I can give you specific information regarding the ttbb in the holodronic, for instance. For instance, we start from particle level jets. We look if a jet is matched to a B hadron, and we call it a B. If not, we look if the jet is matched to a C hadron, but not B hadron, and we call it a B. Then, if the jet is matched to a B hadron, we look if there is one single match, or if there is a match to, and in that case, meaning that one B jet has been lost, or if we have one single jet which is matched to two B hadron. In that case, the jet is very likely associated to gluon splitting. So we try to identify the possible origin of this jet. In fact, you see in the plot that there are categories like ttb, tt2b, ttcc, and tt2b, which refers to what I said earlier, matching to gluon splitting.
Okay, so and all of this is based on ghost matching, right? And it's done in cascade.
Yes.
And then if you don't find if something matches to B or C, then you call it light flavor.
Yeah.
How I was wondering, okay, so this is for the specific analysis question. And all of this then of course is reported in the analysis with these templates, and you do the fit. Now, how similar are the phase spaces that you have chosen for the definition between all had and lepton plus jets and dilepton? I mean, what I'm hinting at is the consistency of the picture that we get from all of them, because this is the real, in my view, the really important message, in addition to the relative sizes of these contributions, which really like the approach of showing both and showing the ratios. But is it different? Can we infer anything about the consistency of the two pictures that we get? In one case, the ttbb, for instance, is about 4.5 picobars, and also in the holodronic, we see a similar value for the cross section. I'm talking about slide 9 and 11.
Yes, yes. For the single lepton, the lepton analysis, the two visible phase space have been chosen differently on purpose, by asking for a different value of the PT of the jets, as you see here. Now, in the holodronic case, the phase phase space is similar to the one chosen for the lepton, if I'm not mistaken. So in this case, you can compare to the lepton results rather than the single lepton results, which has a different threshold on the PT.
Okay, thanks. One final tiny question, if I may, and then I'll let you go because also others have a right to ask a question. Is in your single lepton, just as you mentioned the single lepton, I was forgetting about this. When you do the kinematic fit, you say the first two jets are not included. What does first two mean? Is it are they ordered in PT or?
You have several jets, okay? You do a kinematic fit to the TT bar hypothesis, and you select those jets which match which give the best chi-square, for instance. Then you have additional jets, and the first two in terms of B-tagging score are chosen among the additional jets, are chosen for our analysis.
Okay.
Any other urgent questions? Otherwise, be reminded that we will have some time allocated for general questions right after the last talk. All right. Thank you very much, Andrea.
Thank you.
And we move now to Enrique, who is going to tell us about single top and TT bar associated production with bosons in CMS. Hello, Enrique.
Yes, hello, can you hear me?
Yes, very well. We see your slides.
Okay. So, good morning, everyone. As Maria said, I will present you in the next 15-20 minutes the latest measurements from CMS concerning tt+X and tx production. Before going into the measurement, let me tell you what I will be talking to you about. So in this diagram here, what we are showing is the production cross-section for all the different processes involving top quarks. And the first thing that you can see is that the y-axis spans from 10 to the -3 to 10 to the 3. That is 6 orders of magnitude in picograms. Today, I will not tell you about all these production processes. In particular, what I will show you is the top quark reproduction processes, and this means ttgamma, tzq, ttz, tgamma q, and ttw. And what I would like to highlight is that I will be telling you about processes with cross sections of about 10 to the -1 to 10 picobars as maximum. And the reason why we can start looking at these processes and with some level of precision already is that we have already a good amount of data in hand, and we have to thank the LHC for providing this data. Okay, so let's go into the measurements. The first two that I will show are the production of W-boson or a Z boson in association with a top quark pair. These signatures are among the most massive ones that one can study at LHC, and as I just said, given to the large amount of data, we can already measure them with a fair amount of precision. These signatures are also important backgrounds for other searchers, in particular for TTH, the TTH process in the multi-lepton final states. The ttz production mode in particular is the most sensitive one for measuring the couplings of the top to the set. And these production modes receive significant enhancements in some beyond standard model scenarios. Okay, so the first measurement that I will show is the inclusive measurements of the TTC. For this measurement, we are using the data taken in 2016 and 2017, which amounts to almost 80 inverse femtogram. The baseline selection that we use here, we are requiring exactly 3 or 4 leptons and at least 1 jet. And on top of that, we require that there is at least 1 lepton pair and the two leptons here have to be opposite sign and same flavor, and with a mass consistent with that of the C boson. As you can see in this plot in the right part of the slide, the events are categorized not only as a function of the number of leptons. We have 3 blocks here for 3 lepton events, the last one for 4 lepton events. But we also use the number of jet and beta jet multiplicity in order to further categorize them. So here you can see all the categories that we are using. So in the left-hand side of the plot, we have the 0 beta jet multiplicity, then 1 beta jet multiplicity, more than 1 beta, this for 3 leptons. And then on the right-hand side, we have the 4 lepton case with at least 2 jets. And what you can see here already, which are the signal regions. Basically, the most signal-like regions are the ones with, in the 3 lepton categories, those with at least 1 beta and at least 3 jets. While for the 4 lepton case, it's 2 jets with at least 1 beta. You can see also here that we have nice control regions for the backgrounds, where the main backgrounds here are coming mainly from ttH, ttW, and tWz production. The measurement is done performing a likelihood fit of this distribution, and this can be done independently for the 3 lepton and 4 lepton channel. And the results are shown here in the table. And we perform also a combined measurement of both lepton channels. The main systematics that affect this measurement are, as expected, the lepton identification, that given that we are requiring a large amount of leptons, and also the background normalization. The cross-section that we measure is plotted here. It's 0.95 picoband, that is in agreement with the NLO prediction. And what you can already see here is that the systematic uncertainty that we obtain is already at the same level as the statistical uncertainty. So one step further that we can perform here with this in this channel is to measure it differentially. In particular, what we have done is to measure this cross-section as a function of 2 variables. In the left, you can see the measurement as a function of the transverse momentum of the C boson, and on the right as a function of the angular distribution of the decay lepton. To perform the differential measurement, we restrict ourselves to the most signal-enriched region, and that means exactly 3 leptons, at least 3 jets, and at least 1 beta jet. If we look at the results, we can see that still we have somehow large uncertainties in some of the bins, but still within the uncertainties, we can see that the ANC at NLO generator describes well the shape of the data. The systematics in these differential measurements are similar to the ones of the inclusive. We have lepton ID, jet energy scale, and resolution, and also the non-lepton background. This differential measurement can also be used as an interpretation of the EFTs, and you could see it in yesterday's afternoon session. You could see the results in May's talk. Then moving now to the next measurement, this is the production of a top quark pair in association with a W boson. Here we are using the 2016 dataset, which is around 36 inverse femto band. The baseline selection here is made by 2 leptons with same charge. You can see here in the top right plot the distribution of the number of events as a function of the dilepton category for all the same charge lepton categories. And here our signal, that is ttW, is shown in red. One thing you can see is that basically that the amount of signal is not great. So in order to further discriminate the signal from the background, what you use is a BDT that is shown in this bottom right part of the slide. The input variables for this BDT are the usual suspects, number of jets, number of BTACs, HT, and missing T, among others. And you can see already here in this distribution how this BDT discriminates very well between the signal that is in red and is populating the right-hand side of the distribution from the background, mainly WC and non-brown. So we can use this BDT in order to further classify the events, and this plot in the left is our final distribution, where here the classification first is made in the charge according to the charge of the leptons. We have in the right hand side the negative pairs, and in the right-hand side, the positive proton pairs. Then we also use the BDT as a classification tool. We select events with a BDT value larger or smaller than 0.6. And then we also use the number of jets and number of BTACs. Using this distribution, we can extract a significance of the signal. We observe a 5.3 sigma significance, while we expect a 4.5. And we can also go ahead and measure the cross-section for this process. And here you can see the value that we obtained, 0.77 picobars. That is slightly larger than the NLO prediction, but still within the uncertainties. Again, if you look at the size of the uncertainties, you can already see that the statistical and systematic uncertainties are at the same level, more or less. Talking about uncertainties, the main sources of systematic that affect these measurements are the luminosity, lepton identification, trigger uncertainties, jet energy, and also the non-lepton matter. So now moving to the single top production in association with a C boson. Again, this is a very rare process. It's interesting because it's sensitive to the top C and tt+X boson WWC coupling, and it can show possible deviation from the standard model, indicating physics beyond the standard model. This channel is typically studied in the electronic decay mode, that even if it has a small branching ratio, it's much cleaner than all the other channels. The main backgrounds in these measurements are the signals that I just described in the previous analysis, TTW, TTZ, and also WZ. So the measurement here is done with the 2016 and 2017 data sets. Again, almost 80 inverse femtogram. The event selection in this case is done requiring 3 isolated high PT leptons, and we require one of the pairs to be opposite sign, same flavor, and again consistent with the mass of the C boson. As you can see here in this sketch in the right, here in the y-axis we have the BTAC jet multiplicity, in the x-axis we have the jet multiplicity, and the best signal region is expected to populate this being here, 1 BTAC and at least 2 or 3 jets. Then we also have some signal in this region with more than 4 jets and 1 BTAC, but here we have a large amount of TTC. And then we also have 2 background regions, 1 background control region for WC and CC, the one with 0 BTAC jets, and then we also have another signal region with large TTC. So for each one of these categories, a dedicated boost decision tree is trained, and you can see here in these 2 distributions a couple of input variables of the BDT. In the left, you have the dijet, the maximum of the dijet masses in the event, in the signal region, in the best signal region that we have, and also we have the rapidity of the recovery jet. As you can see in these distributions, one important background that we have to deal with in this analysis is the one coming from non-prompt and fake leptons. And in order to reduce it, we use an MVA classifier that exploits the identification and isolation information. So here I will show in the BDT output for each one of the 3 categories that we are using in the analysis. In the left-hand side of the slide, we have the signal region. And you can see here as the signal in this reddish color is populating the right-hand side of the score, of the BDT score. And another thing that you can see in this distribution is that the right-hand side of part of the distribution is not only has a lot of signal, but the amount of background is really small. If you look at the signal to background region in these last 2 bins, you can see that it's very large. Then the other 2 categories, you can see already that there is some signal already in the 2 of them, but the amount of background is really large compared with the signal region. But still, they can be used to constrain some of the uncertainties in the background. And you can see in all the distributions how the data is very well described by the expectation from Monte Carlo. So we use these 3 distributions in order to extract the significance of the signal. And what we see is a significance well above 5 sigma. And the cross-section that we measure from this distribution is quoted here, is 111 femtobars. That is in agreement with any lower standard model expectation. As an illustration, we are also showing here an interesting variable, that is the transverse momentum of the C boson, selecting events that have a high score BDT output. So this is a very signal-like region, and you can see here the distribution of the data that is within the uncertainties, very well described by the Monte Carlo. The main systematics, again, affecting these measurements are the ones coming from the non-proton lepton background, lepton identification, and also some modeling uncertainties. Now moving to the production of a single top quark in association with a photon. Again, this is a very, very rare process, and it's interesting because it's sensitive to the charge of the top quark and also to the top quark electric and magnetic dipole moments. This measurement is done using 36 inverse femtoband. Here we are looking at the T-channel events, in particular at those events within the muonic decay. So we look at it with 1 muon, 1 photon vicinity, at least 2 jets, and at least 1 tt+jet. In this table here in the left, I'm showing the yields, the expected yields for each one, for the signal, and also for each one of the backgrounds, and also for the data. So I would like to highlight a couple of things here. First of all, you can see that the expected signal is very, very small compared with the total standard model prediction. And also, second, I would like to highlight the main background here is the one coming from the fake from events with a fake photon. And in order to estimate these ones, we are using data-driven techniques. To solve the problem of the low amount of signal compared to the standard model prediction, what we do is to train a BDT that will help us to distinguish the signal from the backgrounds. And we are showing here a couple of input variables to this BDT. You have the rapidity of the light flavor jet, and also the delta between this jet and the photon. And in both cases, you can see that there is a good agreement between the data and the expectation. So here we are showing the output of this BDT. In the zoom, in the inset, in the plot, you can see a zoom of the 3 beams with larger BDT output that are the ones with more signal. You can see how the signal here in green in the last beam is basically the amount of signal is similar compared to is much larger than the background that we have in that beam. That's where all the sensitivity is coming from. So we perform a likelihood fit to this BDT distribution in the signal region and also in a control region for tt plus photon. From these distributions, we can extract the significance of the signal. We observe a 4.4 sigma, while we expect a 3.0 sigma significance. And this constitutes the first evidence of this process. The main systematics in this analysis are the ones coming from jet energy scale and signal modeling. And here you can see the cross-section that we can extract in the fiducial region that is defined by the requirements given in the bottom part of the slide. So moving now to the last part to the last analysis of this presentation. This is the only measurement that I'm showing that is not done with run 2 data. This is using run 1 data at tt+bb. And is the production of tt bar pair in association with a photon. In this analysis, we are using the semi-leptonic decays. In particular, we are requiring the events to have 1 lepton, 1 photon, at least 3 jets, and at least 1 BTAC, and a large amount of vicinity. The main backgrounds in this analysis are the ones coming from the production of tt bar pair plus a fake photon, and also a vector-boson plus a photon. The lepton, we define the lepton plus S fiducial region of the top and the photon. And here you can see in this table below, you can see the measurement separately in the electron channel and also in the muon channel, and also the combined measurement. If you look at the bottom right part of the table, this is the measurement that we have, 515 femtobars. That is in agreement with the uncertainties with the one from theory. So Just to summarize, the large amount of the data that recorded by the experiments provided by the LHC allows us to prove very rare standard model processes with very small production cross-sections. In particular, we are interested in the rare processes involving top quarks, and we are starting to be sensitive to beyond standard model interactions. As you have seen, many processes are explored here for the first time, and all the analysis that we have shown are still not using the full run-to data. And so far, all the results are in good agreement with the standard model prediction. And just let me highlight that what I have shown here, in particular, the first TTC differential cross-section measurement, and the first observation of the T-cell-Q, and also the first evidence of the T-gamma production. As I have said, none of the analysis shown here is using the full run-to data. This is something that is still in the works, so please stay tuned. New results might be are actually underway. Just in case you are interested, you can find more details about all these results in the CMS public webpage. Thank you very much.
Thanks a lot, Enrique. Questions for Enrique? Anyone? Don't be shy. Okay, so I guess the talk was pretty clear.
Okay.
Okay. And thanks a lot, Enrique.
Yeah, welcome.
And then we move on to the next talk, where Knut is going to tell us about top and TD-bar associated production with bosons from the Atlas side.
Yes, can you hear and see me?
We hear and see you. Now we just need to see your slides.
Okay, I hope you can see them now.
Yes, we can.
Okay, welcome to my talk targeting associated production. Oops. Welcome to my talk targeting associated production of top quarks and neutral bosons to probe standard model couplings and search for new physics with the Atlas experiment. First of all, let me briefly reintroduce the top quark. It has a very unique role in the standard model due to its large mass of 173 GeV almost, which means that its Yukawa coupling strength parameter is very close to unity. This also results in a very short lifetime of only 10 to the minus 25 seconds, which means that there are no bound states of the top quark and it decays before hadronizing. For the processes that we're looking at today, the top plus boson processes, we can write down a generalized effective Lagrangian for the corresponding ttv coupling vertex, which could potentially have vector-like structures, axial vector-like structures, so the F1 and F3, but also tensor components reflecting dipole moments of the coupling, such as F2 for the vectorial, the electric dipole moment and the magnetic dipole moment F4 here in that Lagrangian. In terms of the coupling to the photon for fermions, this is purely vectorial, at least according to the tree level in the standard model. And for the coupling to the Z boson, we expect components from the electroweak mixing, from hypercharge and the weak isospin. And both of these only have very minor tensor-like components from higher order loop corrections in the standard model. Now, these couplings are accessible through top quarks in association with a photon or a Z boson. And today I will talk about some first Atlas papers using the full run-2 dataset, which provides stringent tests of the theory predictions. And what I'm presenting here today are two publications of Atlas measurements of ttgamma and tzq production, and an Atlas conference note of ttz production. Let me give you a brief reminder of the Atlas detector. Just very briefly, you can see a a sketch of the ATLAS detector and how the particles traverse through the detector on the left-hand side. From bottom to top, they go through the individual components of the detector, and it has an onion shell-like structure with high precision components such as the tracker in the core, and then the calorimeters and a dedicated muon spectrometer system. The ATLAS detector has an overall very large coverage that some of these measurements exploit up to absolute eta values of 5.0. And we also have 139 inverse femtobarn of data that we qualify as good for physics from the latest run too. Now coming to the first measurement, ttgamma production in the electron-muon channel. Again, the top photon coupling is accessible in the production of these ttgamma final states. However, the problem with ttgamma is that the photon radiation generally is possible by any of the charged particles involved. So experimentally, what we measure as ttgamma production is a combination of all possible scenarios. And you can see on the right-hand side just a few examples. For example, the photon of the ttgamma final state could be produced from the initial state quarks. There could be radiative top production, which is usually what we call the interesting case, because we have a direct coupling between the photon and the top quark somewhere in the diagram. But also any of the charge decay products of the top quark can radiate a photon. Now, there have been earlier measurements at 36 inverse femtobarn with run 2 data published by ATLAS, which looked at both lepton plus jets and dilepton channels and also provided first fiducial inclusive and differential cross sections at 13 TeV. And what I'm presenting to you today is a precision measurement in the EMU channel, where we also again look at a fiducial inclusive cross-section and differential cross-sections in several observables to test a theory prediction. In particular, we are comparing with a fixed order calculation done at next leading order in QCD that became available recently. Now, the caveat with the fixed order computation is that it includes all off-shell contributions and interference effects. So what we actually do is perform a combined ttgamma plus twgamma measurement, where we align the fiducial phase space with the computation. For the inclusive measurement, we perform a bint profile likelihood fit of an observable called ST, which is the scalar sum of all transverse momenta, including the missing transverse momentum due to the 2 neutrinos in the final state. And you can see the bint ST distribution here on the right in the post-fit distribution. Prediction and data agree very well. Then in the fiducial phase space, which on a reconstruction level, we select according to the table at the bottom right. So we ask for 1 electron and 1 muon with large transverse momentum. They have to have opposite electric charge and an invariant mass of at least 15 GeV. We also require 2 or more jets with a radius parameter of 0.4, at least one of which must be B-tagged with an 85% operating efficiency. And we also ask for exactly 1 photon. In this phase space, we then measure a fiducial cross-section with approximately 6% uncertainty that amounts to 39.6 femtobarn, dominated by systematic uncertainties, which is to be compared against the theory value that leaves us at 38.5 femtobarn, which is very well in agreement with what we measure. The dominant uncertainties, as I said, are systematics, and mostly signal and background modeling, but also the ATLAS luminosity determination. We also look at differential cross-sections. So ATLAS data is unfolded to parton level. And again, this is compared against the fixed order, next leading order theory computation, but also leading order plus parton shower Monte Carlo simulations. And we unfold a total of 5 observables: the transverse momentum and absolute rapidity of the photon, the delta eta and delta phi between the 2 leptons, and the delta R between photon and the closest lepton. One example you can see here on the right, which is the absolute cross-section as a function of the photon PT. And within the given uncertainties, you can see good agreement between the unfolded data and the next leading order theory calculation, which generally is true for all variables. However, looking at others, such as this, which is the normalized cross-section as a function of the difference in azimuthal angles between the 2 leptons, again, you can see that the next leading order theory is in good agreement. However, there is some trouble for the leading order plus parton shower Monte Carlo simulation to reflect the shape of this distribution correctly in data. This can also be quantified by chi-square over NDF calculations. And while the fixed order theory calculation has a reasonable p-value in the Pearson chi-square test, the MACRA 5 at leading order plus parton shower algorithms both have p-values that are below 0.01. Coming to the next process that we looked at, which just became available last night, which is ttz production in 3 lepton and 4 lepton final states. And there have been earlier ATLAS measurements at 13 TeV, again using 36 inverse femtobarn, where the inclusive cross-sections of ttw and ttz were measured simultaneously. And this now is a dedicated measurement of the ttz final state with full round 2 data. And the focus here is placed on trilepton and tetralepton final states. And again, we do inclusive and differential cross-section measurements in several observables. And these are unfolded to both parton and particle level. In the trilepton channels, the strategy is to use different regions for inclusive and differential measurements. For the unfolding, there's just one single region to have the maximum statistics available. For the inclusive measurement, there are 2 different BTEC regions to allow for maximum precision and also to suppress the WZ backgrounds. In the tetralepton channels, we use a total of 4 signal regions that distinguish same flavor and opposite flavor lepton pairing and different BTEC multiplicities. There are additional control regions to control the ZZ and WZ backgrounds. You can see 2 example plots of these control regions here on the right. So that leading lepton PT in both cases, one for the ZZ control region and one for the WZ control region, which are backgrounds for the 3 lepton and the 4 lepton signal regions. Now, how do we determine the inclusive cross-section? We perform a simultaneous profile likelihood fit of all trilepton and tetralepton signal regions, plus the background control regions. And you can see post-fit distributions of the 4-lepton signal region combined here at the top right, or of the 3+4 lepton signal region combination here at the bottom. The leading lepton PT at the top and the transverse momentum of the reconstructed Z boson at the bottom. We also cross-check our fit results with the individual channel fits, and what we receive is consistent between trilepton and tetralepton, and the combined signal strength is measured at 1.19, plus minus uncertainties, which results in a measured inclusive TTZ cross-section at 1.05, plus minus uncertainties in picobarn, which is very well in agreement with the next leading order plus next to leading log prediction, which predicts 0.86 plus minus theory uncertainties. Now I picked out just a few of the unfolding variables. There are quite a few of them, but again, this is done both to parton and particle level, and the differential results generally are dominated by statistical uncertainties and uncertainties on the signal modeling and on B tagging. And I picked out here, for example, the transverse momentum of the Z at particle level from the combined 3-lepton, 4-lepton regions, because this is one of the observables that would be sensitive to beyond standard model contributions. And you can see reasonable agreement in this particle level observable here. Then we also looked at the number of jets at particle level in the combined 4-lepton regions, which is also an important variable to look at because the high jet multiplicity region of TTZ production is a background to many more rare analyses. And also the agreement here is quite reasonable. And then we have another variable, which is the delta phi between the reconstructed Z boson and the reconstructed leptonic top quark at parton level. And this is a normalized differential cross-section in the 3-lepton and 2B 3-jet region. And you can see some tension here between data and all of the predictions in those left and right bin here. Okay, coming to the last process that we will talk about today, which is a measurement of single top quark production in association with a Z boson, or just simply TZQ, for which we have seen evidence with the ATLAS experiment using 2015 and 16 data, and the process has been observed by CMS using 2016 and 17 data. Now, this measurement to allow the best signal significance, we only use the tri-lepton channel to to claim the observation that I'm presenting here. This generally is not just tzq, but we also include non-resonant lepton pairs. So in principle, we look for final states such as top and the top quark and another light quark and an opposite sign lepton pair. There are multiple tree-level diagrams, as you can see here on the right. Each of these contributes. So we have contributions from TZ couplings, such as the diagram here at the top, but also ZW couplings, where we have some sort of vector boson fusion into a Z boson for the final state. In total, we define 2 signal regions, one with 2 jets, one with 3 jets, to allow for additional radiation in the final state. And all of these require exactly 1 BTEC jet. Plus, we have additional control regions for the largest background, which is mostly ttz production, diboson, and tt-bar. Now, before looking into the regions that we define in more detail, here's a basic pre-selection that is common to all of them. We ask for 3 leptons with a large transverse momentum, and we must have at least 1 opposite sign, same flavor lepton pair. And the invariant mass of this lepton pair must be below 10 GeV with respect to the Z boson mass. So in the cases where we have mu E final states or E mu final states, this is unambiguous. For the same flavor cases with 3 leptons of the same flavor, we take the pair with the smallest difference to the Z mass. Now for the signal regions, what is particular is this additional forward jet with large large pseudo-rapidity. And then going on from this basic pre-selection, we define different regions according to the number of jets and the number of B-jets. So for the signal region, exactly 1 B-jet and either 2 or 3 jets in total. If we want to move into the control region for diboson, we just place a veto on the B-jets, or into the control regions for ttz, we require an additional BTEC and an additional jets, so that we end up in 3-jet 2B or 4-jet 2B scenarios. For tt-bar control regions, we essentially invert the opposite sign, same flavor requirement and go to an opposite sign, opposite flavor lepton pair, but leave the number of jets and number of B-jets as they were. The normalization of all of these backgrounds is determined through these control regions in the fit, so they're treated as a free-floating parameter. And to enrich the statistics of the fake lepton estimate, which is particularly tt-bar and Z plus jets, we look at dilepton plus 2 BTEC regions. And in these regions, which don't usually have a fake lepton, we replace one of the B-jets with a lepton and also perform a replacement of the energy and polar angle from B-jet to lepton according to truth studies that we performed. Now, how do we obtain the results? We employ neural networks in both signal regions and perform binary event classification essentially. So we have an output test statistics such as these here in the 2 signal regions that we defined. In total, the 2 neural networks use 15 input variables and 1 hidden layer with 25 nodes. And the best separating input variables include things like the invariant mass of the B-jet and the untagged forward jet, or the reconstructed top quark mass. And then we do a simultaneous profile likelihood fit of all signal and control regions, which leaves us a cross-section that we measure at 97 plus minus uncertainties femtobarn, which is very well compatible with the next leading order theory prediction at 102 femtobarn plus minus uncertainties. And the measurement is dominated by statistics, first of all, but also by generally the modeling and the rate of the prompt lepton background. Oops. This brings me to my summary and conclusion slide. So the RAN2 dataset enables precision measurements in the top plus boson topologies. And Atlas has a very rich program of top quark analysis. I just link you the full list of public results again here. And the analysis that I presented today using the full RAN2 data, all of them, was a ttgamma production measurement in the EMU final state, then a ttz production measurement in trilepton and tetralepton final states, and the claimed observation of single top quark production with the Z boson tzq. All of these measurements are in good agreement in inclusive and differential spectra with the standard model predictions. in particular state-of-the-art fixed-order computations and next to leading order plus parton shower Monte Carlo simulations provide good description of the data spectra, as it seems, whereas leading order plus parton shower Monte Carlo simulations have difficulties to describe some of the observables. Now, this first round of ATLAS measurements basically provides a very stringent test of the standard model predictions, and more ATLAS Round 2 measurements are to come in the top quark sector. And here are also the links to the publications. I think the conf note for TTZ will become available immediately. Thank you very much for your attention.
Thank you very much, Knut. I already see some raised hands. So Florencia first.
Oh, hi, good morning. So I have a question. So for the TTZ result, maybe, I mean, it went too fast, the new result that you're presenting on the page 9. So how do I, so how does this analysis, I have two questions. One is, how does this analysis compare with the previous analysis that, I mean, what was done for the TTH and by I don't know, top or whatever it was last year? How does it compare? And then can you also, do you have some backup on the systematic uncertainties on the TTZ?
Available for TTZ production from ATLAS is the 36 inverse femtoband, which is measured basically in conjunction with TTW. And as far as I remember, there are no differential measurements of the final state.
Okay.
So there is just an inclusive TTW, TTZ measurement.
Right.
Both of these were in agreement with the standard model predictions. I don't have the numbers of the old measurement in my slides, but I could provide them to you.
That's fine. And the systematics? Do you have something?
Let me just check if I threw it in here. This was all last minute, last night. Okay, here are the dominant uncertainties. So looking at the systematics here on the right, I hope you can still see them. There's the TTZ parton shower modeling, which is ranked the highest or highest impact uncertainty in terms of systematics, and a couple others related to modeling mostly.
Okay, but then the note will be out today.
Yes. Yeah.
Okay, thank you.
I hope. I let Francesco comment maybe.
Yeah, the note is out already.
I cannot find it. I googled. I mean, it's not in the.
We'll find it.
Wiki. Okay, thanks.
Thomas.
Hi, Thomas speaking here. Thank you, Knut, for a nice talk. I have a couple of questions on this ttgamma measurement, especially on the theoretical prediction there. First, I would like to. So you said that the fact that the theory measurement, theory prediction combines tt gamma and tw gamma is a caveat, but I think it would be very important to turn this around. I mean, after all, we are doing a quantum field theory here, and so we should regard this as an amazing opportunity to test standard model even further. So I think it's an advantage rather than a caveat. After all, theoretically speaking, these two processes cannot be defined separately because of the quantum interference. And
yes.
And I think more and more theoretical predictions like this are going to be coming up in the future. So I think let's try to make this shift.
My point was that it was a caveat for us because it's more difficult to provide Monte Carlo simulations for this kind of process.
Sure.
In terms of theory prediction, of course, this is a much more interesting thing to test. Yes.
Okay, so that was a remark. Then I have a question about the theory predictions that you have that you're using and the existence of the part of the TW in there. I think this calculation is done in 5-flavor scheme.
Yes, I think so. Yes.
And so the TW component would only be at the next to leading order. The TW component would only be included in the real radiation. Is this correct? Because I mean, the TT ttgamma, and so tt bar gamma has a WB, WB, and gamma, and the TW gamma has one B less, right? So then in order to get this final state in a fixed order, you need it to be in the real radiation. So then the TW is going to be only included at leading order. Does this align with your understanding, or?
So actually the fixed order computation computes WB, WB gamma final states. So there is no requirement of any top quark resonances. Yes. Yeah, I mean, TW in principle would only be included with, I mean, it should be even if it's an on-shell top quark, which then decays. The final state always requires the extra B quark. So if it's a next leading order prediction, I think this would be still include next leading order effects on the TWB final state.
Okay, yeah, I have to think about this. Right. So then let me just ask, can you go to the slide where you show the spin correlation, the delta phi distribution? Yeah. So coming back to the discussion we had yesterday in session 2 about this delta phi LL distribution for just for TT bar. How does the consistency between data and theory compares to in this case? I didn't have enough time to look at whether the theory here is more consistent with data than in TT bar sector, or whether the uncertainties are larger, and so there is more space for sort of inconsistencies. Is anyone looking at this? Does anyone know?
I mean, certainly the uncertainties here of the measurement are larger than in TT bar, but generally the tension in TT bar is between next leading order and data, right? So in this case, I think the next leading order agrees in terms of what we expected from TT bar surprisingly well with the distribution.
Yes, I think surprisingly is a good word in there. So maybe there is a lesson there for something we can learn also on the side of TT bar.
It would be interesting to see whether the photon has any impact on the modeling of this variable.
Yes, indeed. Excellent. Thank you.
Yeah.
Jiri has a question.
Yeah, hi, this is Yuri. Just in case there's still some time on slide 10, a question to delta phi in TTZ. And I'm sure you've done many checks, but I was wondering whether this delta phi between Z and the leptonic top was cross-checked with against the hadronic top, or perhaps the lepton, and whether this is a really issue of unfolding to parton level, or whether there could be some reconstruction effect of reconstructing the phi of the tops.
This is a very good question. I'm not an expert on this particular analysis, but I don't know if someone else is connected that could answer this question for you, maybe.
Hi, this is Tom McCarthy from Alice. Yeah, so I think the second part of the question, just in terms of the reconstruction effect, so it was looked at in particular, so not just the delta phi just with the lepton side, but in terms of various levels of reconstruction. So before you add the extra jet and so on, where you kind of just reconstruct the leptonic W before you connect it with a jet, and in that case, it's similar. The agreement there looks fine before unfolding in that sense as well, and so there were several effects which are checked there anyway, but it's only the hadronic top that you were mentioning there that's not done in this case. So it's only the reconstruction of the leptonic side top in this case.
All right, thank you.
Nadje, go ahead.
Hi, I have a very quick question. First of all, congratulations for the nice results. Could you please tell, in addition to the differential distributions that we see here, what are the other observables probably that you have unfolded? Is there anything? is there anything extra to these distributions that we see here for differential, or is that all?
Yeah, there are essentially 9. So it's split up. There's a couple that are combined for the 3-lepton and 4-lepton channels. So the ones you see here, the PT of the Z, also the absolute value of the rapidity of the Z. So the one on the left-hand side here. And then for the other ones, it depends on they're different for 3-lepton and 4-lepton. So for the N-jets, that's done both for 3-lepton and 4-lepton separately, since there's some different numbers of jets in those fundamentally. And then for the 3-lepton, what you see there is the delta phi between the Z and the lepton at top. There's also the absolute rapidity difference between the Z and the lepton at top, because the top is fully reconstructed. Missing one. Yeah, and then in the 4-lepton channel, there is the PT of the TT bar system, which you can do just in the transverse plane in a very straightforward reconstruction with the full reconstruction, and also the PT of the TT bar and the TT bar system, the delta phi between the 2 leptons. So it's something similar to what was shown for the ttgamma.
Right.
Yeah.
Okay, thank you very much. Looking forward to the note then. Thank you.
Robert, do you have a question?
Hello. Yes, I have a question and a comment. The question is, can you repeat again what you said on the availability of the theoretical cross-sections for ttgamma? I think you said it's a BW gamma. Is it this?
Yes, this JHAP publication.
Okay,
I thought it was BW gamma in the EMU final stage. Yes.
Okay, then I have to look again, I think. The comment was, I think your thesis is on arXiv today. Congratulations.
Thank you.
Okay, thank you very much. Any further questions to this talk? And also we open the floor to further questions to the previous talks in case you missed it. Feel free to ask now. I guess Giri and Robert's hands are remaining from before.
Yes, sorry.
Okay, so Thomas, go ahead.
Hi, I just have a question to this tt-bb measurement of CMS. So I saw that the theory predictions that you are using are this TT inclusive, where the BB bar is basically fully modeled by the shower. In the view of sort of a recent plethora of new theoretical predictions which focus on tt-bb final state, what do you think you're going to use any of these predictions in the follow-up analyses? Have you had the time to compare them against data, or have a play with them?
I'm not sure who you are asking the question, Thomas. CMS and Atlas? Anyone from CMS and Atlas?
So there was a talk, I think it was by Andrea.
Yes, okay. So for the CMS case, I mean, there are analyses that are ongoing. We are not going to compare the results that we have with, these are partial data sets anyways, but the analyses that are ongoing in most channels for tt-bb with the full run 2, and at least some of the groups are in contact with theories, as you might know.
Do you know which calculations are used?
But well, right now, I mean, at least one of the groups is in close contact with Pozzorini.
Okay.
But I mean, once that analyses are more advanced and at the level of finalizing, then other comparisons, as always, you know, we want to do the most complete comparisons possible. So we'll go into that as analysis finish.
Okay, thanks.
Actually, in this direction, can you maybe give a bit of a summary of what the various TT plus heavy flavor predictions that are available on the market are, and if you know by when we will have some prediction that will bring them closer together, because they are not agreeing so well among each other.
I presume that's a question to me.
Yeah.
Yes. So there is an as I said, there is a lot of new calculations that are being compared by the authors of the tools. I mean, I think still many years ago there was MATGRAPH, tt+bb at NLOPS. Then Sherpa became available, and then Pauheg and Pauhel and Herwig Matchbox followed up. So this is all NLOPS tt+bb, but there were also new ideas explored with this approach of Frank Siegert and company, where they do so-called fusing, where they combine this tt+jet and tt+bb processes into a single prediction, because this is a truly complicated and multi-scale process, and it does have very important two important production modes per se, right? So you can either consider first the top pair being produced with the jet emission, where the gluon decays into BB bar. So then in this case the sort of jet would be harder. The lighter jet would be harder in the hierarchy, or it can be vice versa, right? And it seems like both regions are very important, and yes, in these comparisons, I think this was noticed in in one of the Higgs cross-section working group comparisons. Some of the tools don't agree very well, especially with respect to the description of these of the extra light jet spectra. So these would be tt+bb predictions, where the light jet would only be described at leading order or leading order plus partner shower. But these differences would propagate back into description of sort of more inclusive quantities. And so recently there was a calculation of tt+bb plus an extra light jet at fixed order by the group of Stefano Pozzorini, and at the moment there is an ongoing effort of trying to tune tt+bb and NL plus PS predictions to the tt+bb-J predictions for the light jet spectra, and we already did a lot of work, but I think last significant progress dates to the ZPW workshop. I think some of you were there, and I think since then we ran out of steam a bit. But I mean, I think this tt+bb-J prediction should give us more indication as to how matching parameters or shower parameters could be constrained in order to make the different NLO plus PS predictions agree really well, and then the experimental community should be able to basically pick any of them, rather than doing a painful comparison of multiple tools and then trying to include their difference into systematic uncertainties.
That sounds really great. So we are very much looking forward to this work. Very nice. Thanks a lot.
Thank you.
Okay. Any other question? If not, then we thank all the speakers from the session for their talks again. And we have a short break and we reconvene at 10. Thanks a lot, everybody.
Thank you.
Hello, everyone. As we said, we would restart at 10 o'clock Prague time. I would like to ask everyone to mute, please. Welcome back to our session. Again, could everyone please check they are muted? Welcome back to our session. So the session now after the coffee break will have a few talks on photon-produced production and also something on probing QED in other experiments. So we will start off with Marta Luszczak on the production of heavy particles via photon-photon processes at the LHC in proton-proton scattering. Marta, could you share your slides, please?
Yes, I'm trying to share. So I have some problems with...
Okay, otherwise we can ask the technical support to share. If they are uploaded, that would be fine. Then you just need to indicate when you want to change the slide. That might be a bit easier for you.
Okay, thank you.
So could the host please share the slides, or should I? I can also do it.
Yes, I can do it. Please wait a minute.
Okay.
Okay, can you see my slides?
Yeah, I see.
Yes,
can you hear me?
Marta, yes, we can hear you, please. Yes, we can hear you, Marta. Please just start. Thank you.
Thank you. The first talk on this session will be about production of heavy particle pairs via photon-photon processes at the LHC in proton-proton scattering. Next. Next, please.
We don't see. Okay.
Okay, thank you. Photon-induced processes in proton-proton interactions have become very topical recently. Precise calculations of various electroweak reactions in PP collisions at the LHC need to account for, on top of the higher order corrections, the effects of photon-induced processes. In this presentation, I want to discuss production of heavy particle pair initiated by photonic subprocesses. I'd like to show you some results of such papers. So I cannot, okay, such papers. We started from production of lepton pairs. Next, we studied production of electroweak bosons in the first step for collinear approach, and the next for so-called KT factorization approach, in which we included transverse momenta of incoming photons. Finally, I will show you some results for tt bar. Next. At the beginning, on this slide, on this slide, I put general diagrams for inclusive photon-photon to WW mechanism. We know that photon-photon processes contribute also to inclusive cross-section. The first one we look at diagrams. The first one is for inelastic component to WW in the final state. The middle is for elastic contributions to WW. The last one is for inelastic to WW in the final state. Below, we can see corresponding formulas for inclusive cross-sections. The first panel corresponds to the first equation, the second for second equation, and the last one corresponds to the last equation for inelastic component. Next. We used our calculations the following photon-parton distribution functions, MRST, QED parton distributions. This is QED corrected evolution equations for the parton distribution of the proton. The last one is for photon distribution. We used also the NN-PDF parton distribution, which is based on fit to deep inelastic scattering and Rayleigh data. Recently, very popular is LUXE QED parton distributions, which is integral over proton structure functions F2 and FL. Next. In order to better understand the role of photon processes in production of heavy particle, I would like to start with our first results on this. We see distribution in PT, transverse momenta, in rapidity, and below in invariant masses. We compare all 4 photonic contributions, black lines, with dominant mechanism. Green lines are for dominant processes. We see quark anti-quark annihilation, solid line, and gluon-gluon fusion, dashed line. We compare such dominant processes with photonic contribution, and we see, if you look at distribution in invariant masses, we see that photon-photon to WW subprocess are very important contribution to large invariant masses. Next. Here we see the same distribution in invariant masses for NN-PDF's QED photon distribution. Black line is for standard MRST photon distribution. The red lines are for dashed are for NN-PDF photon-parton distribution. We observe big uncertainties, especially for large WW invariant masses. This is important. I mean, in the region, this is the region where searches for anomalous boson couplings are studied. I can say that very difficult to obtain the photon distributions from feeds to experimental data. Next. Now we can see formula for KT factorization approach. I mean by KT factorization approach that we included transverse momenta of incoming photons to our process. In the context of the big uncertainties for collinear approach. We had to include the unintegrated photon fluxes, which can be expressed in terms of the hadronic tensor. Next, the unintegrated photon fluxes enter to the cross-section for W plus minus production. The X1 and X2 are the longitudinal momentum fractions of WW and are obtained from the rapidities and transverse momenta of final state. Next. Now we can see unintegrated photon fluxes, the inelastic fluxes and elastic pieces. I don't want to discuss details of our calculations, and we can skip this slide. Now I'm coming to our results for integrated cross-section. We see in this table cross-sections in picobar for different contributions and different F2 structure functions looks like ALM and Surieni compared to relevant collinear distribution with MRS TQED and LUXE QED distribution. One can see that the largest inelastic component is in all calculations systematically bigger than the elastic component, which gives the smallest contribution. We obtain cross-section of about 1 picobarn at 8 TeV and 1.8 picobarn and 13 TeV. This shows that the two photon production constitutes only about 2% of the total cross-section. However, its relative contribution, as well mentioned, increases with invariant masses. Next. Now we see our results for KT factorization approach. Upper panels show the distribution of the mass of the proton remnants. We see for different structure functions looks like ALM and Surieni for 8 TeV left panel and 13 TeV right panel. We see quite large invariant masses of remnant system are generated. Bottom panels show the inelastic show different components: inelastic red, elastic blue, inelastic also blue, and elastic green contributions to WW invariant mass distributions for the KT factorization approach with LUXE like structure functions, and compared to the relevant distribution for collinear approach with similar structure function LUXE QED. What we see, there are large uncertainties in the region of large invariant masses. At low invariant masses, there is relatively small theoretical uncertainties. The next. Now I want to show you some results for spin decomposition. In the table, we see contributions of different polarization of W bosons for the inelastic component for the LUXE light structure function. The cross-section are given in picobarn. Below, we see distribution in invariant masses for all different polarization. It can be seen that TT, both W's are transversely polarized. The TT component is larger than 80%. LL, when both W's longitudinally polarized, LL component plays a special role in studies of WW interactions. However, in the photon-photon fusion, the cross-section for production of this component is smaller than about 5% of the total cross-section. Next. Now I'm coming to our calculation, our results for rapidity gap survival factors caused by remnant fragmentation. Our main aim to estimate gap survival factor associated with the remnant hadronization, which destroys the rapidity gap. We see the situation on diagrams. We use an implementation of above process in SEPGEN for Monte Carlo generated of unweighted events. In the next step, the hadronization of remnant states X or Y systems is performed using the Lund fragmentation algorithm implemented in PTA8 and interface to SEPGEN. So we model the incoming photon as emitted from a valence quark collinear to incoming proton direction. The next, next. Next. Can you hear me? Okay, thank you. In the first step, we have calculated the gap survival factor on the parton level. We see the formula for the gap survival factor, which is defined as you see. The sigma, this part, the sigma eta jet, is the rapidity distribution of the cross section for W production as a function of rapidity of extra jet. By extra jet, I mean de facto parton. Sigma is the associated integrated cross section. In figure below, we show this eta jet as a function of this rapidity distribution of the cross section. If you look at the figure, no extra cuts are imposed here. We get a very broad distribution in eta jet, C solid line. However, a leading order parametrization may be used to disentangle the partonic contribution to F2 for Q square more than 9 GV in square. For illustration, we show the contribution of valence dashed line and C dot line components. As can be seen, rapidity distribution for different components are very different. The C component is important for larger rapidities than the valence one. The next one. We consider separately the case of double dissociation as well as the case of single dissociation. Now we see distribution in pseudo rapidity of particles from X and Y for different ranges of masses of the centrally produced system. The red squares are the region relevant for ATLAS and CMS pseudo-rapidity covered. The next. Now we see gap survival factor for double dissociation as a function of the size of pseudo-rapidity veto applied on charged particles emitted from proton remnants. We predict a very strong dependence on eta cut. I can say it would be valuable to perform experimental measurements with different eta cuts. Next. Now we see eta charge distribution for single dissociative process for 4 different windows. We can see these windows for 8 TeV for LHC energy, for 8 TeV left panel and 13 TeV right panel. This lines show pseudo-rapidity coverage of ATLAS and or CMR's detector. The next. Now we see distribution in eta cut for single dissociative process. The value of for different windows and for 2 LHC energies, we see and we have calculated that the value of gap survival factor for double dissociative is almost the same as the value for a single dissociative gap survival in square. The next. Okay. Now we see the dependence of the rapidity gap survival factor on mass of the dissociated hadronic system. We observe that for eta cut value of 2.5, the rapidity gap survival factor stays very close to 1. For mx, below 100 GeV. We see that increasing the mass of the dissociative system leads to gradually destroying of the pseudo-rapidity gap. Arbitrary
It is time to slowly wrap up.
Okay, thank you. When eta in the region -2.2 to point. Finally, I want to show our results for production of tt per production. Here you see the general diagrams. Next. Now we see in this table, we see cross-section in femtobarn at 13 TeV for different components, left column, and the same when the extra condition on the outgoing jet is imposed. Right panel results with a rapidity gap in the central region for -2.5 2.5 is required in addition. What I mean by require in addition, that means no additional particle production expect to tt bar T or T in the final state. Next. Now we see distribution in outgoing proton remnant masses mx or my. Now we can see for mx. We see that population of large ms masses is associated with the emission of jet visible in central detectors. The rapidity gap requirement introduced a rather sharp cutoff in the large masses tail of the mx distribution. Next. Also, our results for tt bar per production. Now we see distribution in mx for a fixed my, left panel, and in distribution in my for a fixed mx right panel. The distribution are arbitrarily normalized to the same integral. We see that all the distribution coincidence. This means that the two-dimensional distribution can be factorized. The next one. Now we see distribution in mass of pair of tt bar. The conditions of outgoing light quark, anti-quark jets are imposed. The extra condition leads to a lowering of the cross-section with only very small modification of the shape of mass of tt bar. The next one. My conclusions. We have discussed the quantity called remnant gap survival factor for proton-proton to W plus minus and proton-proton to tt bar reaction initiated via photon-photon fusion. We use a recent formalism developed for the inclusive, which includes transverse momenta of incoming photons. First, we have calculated the gap survival factor for single dissociative process on the parton level. In such an approach, the outgoing parton, I mean jet mini-jet, is responsible for destroying the rapidity gap. We have found that the hadronization only merely modifies the gap survival factor calculated on the parton level. This may justify approximate treatment of hadronization of remnant. Thank you. Thank you.
Thank you very much for this nice presentation, despite the technical difficulties. I would suggest we take the time to have maximum one question and refer the rest of the discussion either to the general discussion after the session or to the photon-photon discussion that we will have this afternoon at 12:45 or 12:55, sorry.
Okay.
Any questions? Yes, I hear someone unmuted. Please go ahead.
Yes, Mark, that's a very short comment concerning slide 17. Survival factors do not factorize.
Hi, Valerie. Wait.
Hi.
Hi. Yes.
There are no such conditions.
Yes.
So it was very short.
Yeah. Yes. Yes, you're right.
Okay, thanks a lot. I guess we'll keep this also a little bit for the discussion in mind later today. Then I would suggest thanks again to the speaker. Thanks again, Marta. We'll for sure have time to discuss this a little bit later. Thanks again for your talk. And now I would like to ask the next speaker to share his slides. Yeah. Noam? Okay, yes, sure, we can hear you. It seems a bit faint, but if you speak up, that will be fine. Please go ahead. Thanks a lot.
All right. So I'm going to talk about the LUXE experiment. This is a new experiment in DAISY, Hamburg. Very different from the LHC, but I'm sure you'll find it interesting in the context of ICHEP. Okay. So the outline is basic introduction of the subject, very general, then layout and predictions for the experiment, and then a bit about new physics opportunities, and then the experimental design very briefly, and a summary. So just to introduce the subject, so if you don't know what happens in strong fields, so you can imagine that you have a huge plate capacitor that you know from textbooks. And imagine that you have an infinite amount of voltage that you can apply. So in principle, you can generate infinite electric field. And if all that is immersed is basically placed in vacuum, then still the vacuum fluctuations will be separated, basically, as you can see. So the virtual photons that always fluctuate would be separated to virtual pairs. And this field is very, very large. So this was calculated by Schwinger in the 1950s, and it's 1.32 10 to the 18 volt per meter. Now, the probability to materialize one virtual pair from the vacuum is proportional to the ratio between this Schwinger field and the actual field that you apply. And as you can see, maybe it's not very clear, but there is a lot more about that in the background. In the backup slide, this is basically non-perturbative with very, very large fields. So the Hawking equivalent, I'm sure you all know that, but let me just briefly say that if you go close to the event horizon of a black hole, then and basically you have a very, very strong gravitational field, which is equivalent to our case to the electric field, and basically you can again break these pairs from the vacuum, and this is the mechanism by which the black holes evaporate, and this is called the Hawking radiation. So about a bit about the history and the impact of the field, because it's very different from what we've heard so far in the morning. So in the 30s, there were the first discussions by Sauter, Heisenberg, and Euler. Then in the first calculation was done by Schwinger in the 50s. Then only in the 90s, it's like they were able to approach this field in an experiment, which I will describe later. And then we are talking about the 20s now, 30 years later almost. To reach basically this Schwinger field and beyond, but I should put a disclaimer here. We are not going to produce, of course, such a huge field, but when you go to boosted systems, then the boost enhances the field that you generate by laser, let's say, and then you basically can reach these kinds of fields at the rest frame of the particles that you are dealing with. So this has never been done in a clean environment. Of course, this exists everywhere in the universe, in many phenomena, but it is a basic test of predictions in a very, very novel quantum mechanical regime, very different from the perturbative world that we work in the LXC. So I'm basically also an Atlas person, so I know the two worlds. There is potential for seeing effects of new physics here, and it is relevant for many areas in physics, and I list just a bunch of areas. So neutron stars, where you have very, very strong magnetic fields rotating, generating very strong effective electric fields. So Hawking radiation we touched, inflation, electrical breakdown, and also in colliders. So the physics in a nutshell in LUXE is basically what I said earlier, is that we cannot produce this kind of very strong fields, electrostatic fields, but what we can do is collide, for example, a high intensity laser pulses with very energetic electron beam. And this is what we are going to do in the experiment. We have a very energetic electron beam, and we collide it with a high intensity laser pulse. And basically, the electrons come from the XFEL accelerator in Hamburg. And the laser we were going to, of course, have 40 terawatts to something like 350 terawatts. And then you basically produce, in the first setup, you have nonlinear Compton scattering, which means that you basically, the electron swallows several laser photons and then emits the Compton photon. Then this Compton photon also swallows a few photons from the laser and produces the E plus E minus pair. We can, of course, do that directly with a Bremsstrahlung photon if we convert the electron beam to photon beam, just putting a foil, a thin foil with a high Z material, and then basically start everything from the photon itself, but the physics is the same. So a bit about the layout. Here we're talking about the XFEL accelerator in Hamburg. So this is, as you can see, sorry. As you can see it on the top right, this is Daisy, and then the XFEL fan, which is given in the middle plot. This is where all the photon science experiments are located at the end of the tunnel. So the tunnel starts from Daisy, and we are going to be located approximately here, where you see the LUXE circuit. The point again is that we enhance the field that we already generate with the high intensity laser by a factor of 10,000 approximately. So this depends on the exact energy of the electrons, etc. But you can see it's basically enhanced by a factor of the photon energy to the mass of the electron. So about 10 GeV over half an MeV. So 10,000 times stronger. So this brings you basically to the frame that you're interested in, where physics happens, then to have a field which is stronger, basically can be stronger than the Schwinger field. We have submitted the letter of intent for the experiment. This is basically a synergy of particle physicists and laser physicists, so strong field theorists and beyond the standard model phenomenologists, and also experimentalists from Atlas. You will recognize some of the names here, surely. And it's very cool, and it's not so large. So we are talking about 17.5 GeV electrons with something like a billion electrons per bunch. And we can have basically, if we take one bunch from a train, then at a rate of 1 Hertz, because this is driven by the laser repetition rate, then basically we can do all the physics of the experiment. The laser itself is, as I said, it's going to be 40 terabytes in the beginning, but we are looking forward to the future to go to 350 terabytes. This is a huge amount of power. And the intensity, this is the figure of merit here, would be 10 to the 19 approximately watt per centimeter square, to basically 2 orders of magnitude higher than that. Okay, so the experimental setup in very sketchy lines, let's say. So if you look on the first setup, this is the Compton scattering that I was describing in the first pages. So you have the electron beam coming from the left, you collide it with the laser at the interaction point, and then you produce basically the E plus E minus pairs. You separate the pairs using a dipole magnet, and then you have an array of detectors, basically a pixel tracking detector, a calorimeter behind it, and because here we expect also the beam electrons we have a huge beam with 1 billion electrons per bunch, basically. So we have to dump it somehow, and also the rate would be enormous. And as you can see, at the first plane of the detector, this is how it's going to look like. It's very small spatially, but the rate, as you can see, is like 10 to the 9 electron on the electron side. So you cannot work with a tracker with the normal detectors. You need to go to something which can absorb this kind of rate. On the other experimental setup, as I said, we can convert the electron beam to photons and basically remove the electrons already at the beginning and just have the photons interact with the laser. Of course, this won't be a monochromatic beam, but still this is very useful and nice and clean. So here we're talking about order of magnitude 10 to 2, basically 100 particles per interaction. So this is very manageable, and here we are going to have a tracker on both sides and calorimeter on both sides. If I will have time, I will also touch the forward system for the photons that anyway continue. So reaching the Schwinger field at the particles rest frame, this is what we want to do. We will do that by measuring the rate, the E plus minus production rate, and the Compton photon production rate. This is characterized basically by dimensionless parameters. One is the laser intensity. This has nothing to do with the interaction itself, and this is proportional. This is psi parameter, and it is proportional to the ratio between the field and the Schwinger field. The same parameter basically appears in the probability to produce a pair from the vacuum that I was mentioning in the beginning. The second parameter is the quantum parameter. Sometimes it's called also the recoil parameter. And this is already depending on the boost, basically, as you can see. So it depends on the energy of the electron or the photon divided by the mass of the electron. And then it is also proportional to the same psi variable, which is the ratio between the two fields. So the E144 experiment at SLAC in the 90s, they were doing only the electron laser setup, and they have achieved something like a quarter of the Schwinger field, and again, the rest frame of the particles. And this was a milestone for physics, basically, and it was a very important experiment. But since then, you can imagine that we have gone a very long way with the lasers, particularly. So and this is what we're exploiting now. So the two measurements that we're going to do are basically the rates, and you can see how this looks like basically on the left, and the Compton rates on the right. If I will have time, I will get to that weird shapes here that you see. This is called Compton edges, but we're focusing mostly on the E plus and minus rates. On the top, you can see what SLAC were able to achieve. And this is still well in the perturbative regime, so and it's well described by theory, although it's non-linear. So they do absorb several photons from the field. About new physics, what we can do with LUXE. So here I'm talking just about one option. We're exploring several, but this is looking feasible so far. So axion-like particles, for example, can have couplings to photons and also to electrons. What I'm showing here is just the first part of the couplings to photons. And if we take an ALP with a mass of Ma and the photon coupling 1/λ, then you can see basically what we can achieve. So I will briefly describe what we're looking at basically here. So this is just a conceptual drawing, and it's being proposed now, and we have to see how to implement that. But you are starting with the electrons, again, collided with the high intensity laser, and you produce the Compton photons, but this production is non-perturbative, and that's the key point, because as you can see on the top plot, the rate is higher by 2 orders of magnitude than the rate that you would produce by just converting the electrons to photons with a foil, so non-perturbative production. This is the green shape, and the black shape, this is the non-perturbative production of the Compton photons. So basically you gain a lot by that, but this is not different from a beam dump, other than that, from a beam dump experiment. But of course, it's very important that you have this kind of rate, because that's the whole point. Then you convert basically on the target, you let the photons collide with the target. It's again a thin foil, and then you produce the ALP. You kill all the photons with some shielding, and then the ALP decays somewhere after the shielding and between and before the detector, basically. And as you can see, if you put all that numbers in naively, then this is what you would be able to do, and this is very competitive, we would say, for comparing to phaser 2, which is only supposed to be getting its desensitivity at the end of the high luminosity LHC. And also SHIP it's not clear whether or not this is going to happen. The same for Sequest. So we have a lot
3
of
minutes left.
Sorry,
3 minutes left.
Yeah,
3 minutes left.
So we can cover. Okay, so talking about the laser briefly. So we have already a 40 terawatt laser, which is loaned to us by Jena. And in phase 2, basically, this is phase 1. Phase 2, we are looking up towards 350 terawatt laser. The challenge here is to know the exact intensity at the interaction point, where the laser is basically being tens of meters away from it, and with a remote diagnostic system. So you can see how it is in the design now. This is the laser room, this is the interaction point. The challenge here is to measure the parameters to infer the intensity, and the intensity is basically the pulse energy divided by the pulse spot size and the pulse duration. And of course, small fluctuation in the intensity lead to large fluctuation in the rate which we want to measure. So you have to either increase the stability by a better design, or come up with the precision diagnostics per shot. You can see how this ideal Gaussian pulse looks like, and how a real pulse looks like in the black curves. About the detector, so very briefly, so this is, if we look from the other side of the experiment, so we have the dipole and the electrons or the photons coming from the left. Then we have a vacuum chamber and an array of detectors, so the tracker that I was mentioning earlier, the calorimeter, and the Cherenkov system. These are all going to be based on relatively off-the-shelf technology, so the Alpine from Alice ITS upgrade, and basically calorimeter from Lumical, ILC Lumical, and Cherenkov from the ILC polarimeter. So this is just to show off a bit. I won't go into too many details here. It's just to show that we have in simulation and evaluated the performance of this detector. So the tracker would provide very high efficiency with very small resolution in energy and very small resolution in spatial position. Also, the calorimeter would have a very good efficiency and good spatial resolution. And same for the Cherenkov. This I think I would skip, and just one last word about the synchronization. This is basically the world's largest femtosecond precision synchronization system, and you can see that after like kilometers, you can reach a sub 10 femtosecond precision in timing, and this is going to be very important for us. Of course, that would be triggering our laser, and the laser in turn would be triggering the detectors to take out the data. And summary slide. So we are going to approach and pass the Schwinger field in the particle's rest frame in a clean environment for the first time. Strong field effects may enhance the potential to uncover new physics, and this is very interesting and has a lot of potential. The collaboration is pretty open for contribution, so if you're interested, just drop me an email. You can see that the timeline, basically, we're talking about starting to install really next year and then start taking data in 2023, something like that. First with this Yeti 40 laser and then the 350 terawatt laser. So this is all the institutions participating so far, and that's it. Thank you.
Thank you very much. Thank you very much, Noam. And we have time for some questions. Are there any questions? If there's any, then okay. I have a question. Now, this is a very naive question. But I think it's not quite on the slide. So the photon energies that you reach roughly have a cutoff, I mean, translating now into particle, more like collider physics people. So the cutoff is more like at 10 GeV or so for the photons?
Yes, because imagine the energy that you pump in is coming basically from the XFEL accelerator, and this is at maximum it is 17.5 GeV. So if you convert this on a foil, then you would get something at most 17 GeV, and but of course less than that. And the Compton photons that you can see, it's on average, let's say 2 GeV. Or at maximum 10 GeV.
Okay. Okay, thanks.
This is you can see it here on the plot that I'm sharing now, so on the left.
Yeah. But so you don't have any way in this setup to, let's say, collide photon on photon, right? This is this is just photon on target.
No. It is on per se laser versus photon basically interaction. So because you collide the laser photons with the Compton photons or the Bremsstrahlung photons, but this the laser photons, it's a bit confusing because we consider this as a classical field basically. So but you can talk in two terms, the classical and the quantum terms, and you talk about how many laser photons the Compton photon is swallowed, or you can talk about the field basically that the Compton photon is experiencing.
Okay. So you also cannot really talk about the center of mass energy between the laser field or the laser photons and the photon beam.
Well, you can, but it's very, very boosted. So that's where we get all the enhancement basically. So you can talk about this center of mass frame basically. That's what you.
So what would be the center of mass energy between the photon-photon system?
I have to calculate it. I can't dig it out of the top of my head, but this is easy. I will do it later for the discussion.
Okay, thanks. So this we can then also maybe put on the MetaMost or so, and also discuss later. Are there any other questions? Yes.
Well, I can just comment. I mean, it's order 1 MeV. It's order 1 MeV.
Okay. Okay. Just to get a feeling, right? I assumed it was quite low, but
it is low because the wavelength of the laser is it's 800 nanometers. So we're talking about EV photons from the laser basically. EV photons versus GV photons, right? From the beam.
Yeah. Okay. Thanks a lot.
All right.
All right. Any other questions? Otherwise, I would say we will move on to the next speaker. Thank you, Noam, again, who's Mateusz Dyndal, and he's going to talk about measurements of photon-photon fusion at the ATLAS experiment. Mateusz, can you share your slides?
Yes, I will. Can you hear me and see me, hopefully?
Yes, we can see you.
Perfect.
Hello.
Hi. Do you see the screen now?
Yes, we see the slides now. That seems to be working fine. Thanks a lot. Please go ahead.
Okay, thank you. So I'm going to talk about recent measurements of photon-photon fusion at ATLAS. For a few words of introduction, let me just remind you a very old idea of Fermi, a very brilliant idea, basically. So to initialize this type of interaction, we are using the fact that boosted charge particles are pretty intense, or can be pretty intense source of photons. So we can just transform this collision of electromagnetic fields into a collision of a quasi-real photon fluxes. And there are basically some differences between the lead-lead and the PP photon fluxes. So in the lead-lead case, the overall flux is much softer. However, it's much more intense at lower invariant masses of a diphoton system. Whereas in the PP case, it gives us an access to higher energy phenomena. Basically, the cutoff for proton beam is around 2 TeV for a single maximum energy. Concerning the experimental approach, we are dealing with the exclusive final states, and therefore the exclusivity requirements are pretty essential here. Fortunately, in ATLAS, we have many subdetectors available, which cover almost entire solid angle around the interaction point. Another interesting feature is that, the outgoing ions escape into a beam pipe, so we cannot probe them directly. They only occasionally emit some neutrons, which we can detect in 0-degree colorimeters. However, for the protons, we can tag them and measure their properties in dedicated stations, which we have. We have ATLAS for proton detectors. And another important fact is to take into account for proton and ion dissociation. So sometimes it could be a background, or in most of the cases, we can also treat it as a signal because it's still like a photon-induced dissociation. So this is an outline of my talk. So I'm going to present a very fresh measurements concerning 2 photon fusion processes. I'm going to start with the lead-lead collision data measurements, including dimuon and light-by-light scattering measurements. And then I move to PP collision data, where we have a nice observation of a proton scattering in association with lepton pairs, and then the observation of a photon-induced WW production. Let me start with the exclusive dimuons in lead-lead. So this is a very standard candle process, which allows us to probe in details the initial photon fluxes and also higher order corrections. What we do in this particular measurement is first we categorize our events with respect to the ZDC activity. So the ZDC energy on either side is shown in this nice scatter plot. So we consider 0 and 0 in topology where we do not see a big activity in ZDC. And then 0 and XN and XN, XN. These are the categories that are set whenever we see some activity on either side of ZDC. Then second important fact is that we need to model well the signal and background processes. For the signal, we are using a combination of starlight and tt+8. And then we have also identified a pretty important source of background, which is the semi-coherent production via the virtual photon exchange. So here we model it with LPER. So this is the way how we subtract this background. We basically fit a template to the accoplanarity distribution of the 2 muons, and we extract the fractions, which are basically 0 for the 0 and 0 in category, but it can be non-negligible at the other event categories. we have measured differential cross-section as a function of several variables. So, for example, this plot shows you the accoplanarity distribution, where you can clearly see that when we account for FSR corrections in PTI8, it really improves the description of the tail of the accoplanarity distribution. But in general, the measurement is in reasonable agreement with starlight. We do see some disagreements, which are happening mostly at large diameter rapidities, and we also translate these disagreements into using this simple transformation into the minimum and maximum photon energy, because we have ambiguity in this process, and you can clearly see that the disagreement mostly happens at lower initial photon energies and the highest initial photon energies. So this is a nice way to probe the initial photon fluxes in details. Then another set of measurements have been made for the measuring the event fractions with activity in ZDC. So this measurement is sensitive to extra Coulomb interactions that can happen between the colliding ions. And the important fact here is that our measurement needs to be corrected for electromagnetic pileup contribution. So this particular effect is demonstrated here. So the open points shows you the raw data, and then the corrected data as a full point. So there's a clear difference between the two. But more importantly, we are also comparing our results with respect to the starlight predictions. And in general, we observe less fragmentation in data with respect to the starlight. So this serves a nice benchmark for the future tuning of our Monte Carlo generators. Now, the next interesting measurement is the follow-up measurement for the light-by-light scattering. Just to remind you, this is a very rare process that occurs via this kind of loop diagram, which is also, by the way, very sensitive to BSM physics. And the previous LHC measurements were focused on establishing the first observation of this process. And this particular new analysis covers the exploration of differential cross-sections and also the specific interpretations in terms of search for the axon-like particles. So what is nice in this measurement is that our detectors are really pushed to the limits. So we have a very low T photons. We start at 2.5 GeV, and we veto track activity down to 50 MeV, which is extremely small value. And this plot shows you how we basically deal with the various backgrounds. So this is the gamma-gamma coplanarity distribution. Our signal sits around here, whereas the tail of the distribution serves as a nice control region to normalize our dominant backgrounds contributions, which are dominated by misidentified gamma-gamma to E and also the central exclusive production via three-gluon exchanges. So both of these contributions are estimated using data-driven methods, which is very nice. So then we also measure the cross sections. We measure both fiducia and differential as a function of several kinematic variables of outgoing photons. And these are the two examples. So this is the M gamma gamma distribution, and this is a cosine theta star distribution, where you can clearly see that so the shapes are in a reasonable agreement, but we have a global 1.7 sigma deviation between the predictions and the measurement with respect to the overall fiducia cross section. We also do a search for the axon-like particles. So what we do here, we just treat the standard model light-by-light production as a background together with the other sources of minor backgrounds, and then we simulate our signal hypothesis using starlight for various axon-like particle mass points. At the end of the day, we extract the limits on the cross-section for axon-like particle production via this particular channel. But more importantly, we also translate these limits into the limits on the axion photon-photon coupling. And then we can also assume that the Bragg fraction of axion-like particle to photons is close to unity. And we can also compare with the other previous measurements. And you can clearly see that in this specific mass range of 6 to 100 GeV, which we probe, we have the best sensitivity so far comparing to the other measurements. Okay, let me switch the collision system a bit to proton-proton case. we have a nice Atlas forward proton detectors, which we have fully installed in April 2017. So these detectors are housed in dedicated Raman pods, and they consist of 4 stations, a pair of near station, which houses the silicon tracker, and a pair of far station, which houses both silicon tracker and the time of flight detector. And we basically use this spectrometer to tag the outgoing protons from the 2 photon induced reaction. So we have started with the basic measurement of exclusive dileptons with AFP proton tag. So here, one important fact is that we treat the exclusive and the single dissociative production as a signal. So we're using around 14.6 inverse femtobarn on 13 TeV PP data. And the very important facts that come from this analysis is that we had to do quite pioneering work in order to understand a new detector. So this work includes both proton reconstruction, the improvements for the reconstruction efficiencies, and also the detector alignment. So in particular for this part, we are using in situ corrections that are based on the same selected diamond events. So the procedure is also demonstrated a bit here. What is shown on these plots, this is the proton energy loss as calculated by the AFP spectrometer, and this is a difference between the proton energy loss that is calculated from the dilepton system kinematics. So we do these corrections to minimize basically the distance between the two, and we know that our signal should lie in around 0. And we also use this fact to suppress the remaining backgrounds, which are mostly combinatoric. So it was really discussed in details today by Jesse. So I also refer to his slides here. As I just mentioned, the background is dominated by Drayland plus PyLab combinatorics. So we are using a fully data-driven method to estimate that. And on top of that, we also validated in a dedicated control region around the Z-boson peak mass. Which is shown here. So this is a same Xi difference between the AFP and the dilepton kinematics, and the light blue part shows you the estimated size of the combinatorics, which nicely follows the trend observed in the data. What we do to extract our signal events is that we require a relatively small difference between the Xi AFP and the Xi of a dilepton below 0.005. So this is a simple kinematic matching, which cleans out nicely events from the inclusive background. And this 2D map, MLL, YLL map, shows you the features of the signal candidates with overlaid acceptance for both site A and site C AFP detectors. We have measured fiducial cross-section in slightly tighter Xi range as comparing to the plot I've shown on the previous slides. So these are the main event properties in this signal region. So the plot on the left shows you the ecoplanarity distribution of dileptons in the case of muons. We can clearly see that the exclusive part features this nicely peak structure. And then on the plot on the right, this is the dilepton invariant mass distribution. Again, nicely follows the predictions. At the end, we compare our results with respect to the different proton soft survival models. So you can clearly see here. So we just split the fiducial cross-section measurement into E and mu parts, and you can clearly see, first of all, we have some slight difference between the phase space between E and mu. That's why these two fiducial cross-section are different. And then you can also see that if you compare the measurement with respect to the different soft survival models, the data really prefers the presence of the soft survival factors here. Another interesting measurement that has been made in PP collisions is the gamma-gamma to WW scattering measurement. This is a pretty rare electroweak process that nicely probes these quartic interactions in the standard model. So we have a new measurement that exploits 4 and 2 PP data sets, which is a follow-up on run 1 evidence measurements from both Atlas and CMS. So the main ideas for this measurement is, first of all, we tag EMU pairs with a PT of a EMU above 30 GeV, just to take into account the presence of neutrinos. And then we also rely on the fact that we should not see any track activity near reconstructed lepton vertex. Unfortunately, we do not have yet the results which utilize the AFP tag, but the single tracking veto was sufficient to observe this nice process. So the main backgrounds for this process are the QCD-induced WW production, and the main challenge here is to have a good physics modeling of events with a small particle activity. So this includes both underlying events and also a good modeling of the pileup. So the plot on the right shows you the number of reconstructed tracks. And the first bin is basically a signal region where we do not see any other tracking activity, whereas the remaining entries on this histogram serves as a nice control region to constrain the inclusive backgrounds. We had to derive a dedicated corrections, first of all, to model better our background. So the first correction is the underlying event correction. So here what we do, we reweight our inclusive backgrounds with respect to the charged particle activity spectrum that is derived using a Drellian events around the ZPIC region. So this is nicely demonstrated on the plot on the left, where the uncorrected predictions for the Monte Carlo generators are shown as a dashed lines. You can clearly see large disagreements, which disappears after we apply this dedicated correction. The second type of correction, which also needs to be taken into account, is the pileup correction. So here we basically correct the activity of the pileup tracks, which can be occasionally randomly associated with the interaction vertex. So for that purpose, we have developed a data-driven technique that we are using, and the plot on the right shows you the density of these pileup tracks. So the distribution peaks at 0, but occasionally we can have some extra tracks associated with the vertex. And this plot also shows you how uncorrected Monte Carlo performs with respect to the data. And then after applying several sets of corrections, we can also nicely model this distribution in the simulation. Concerning the signal, we had also derived a similar set of dedicated corrections. So it's takes into account both the exclusive efficiency correction. So we are using the same data-driven method to estimate that efficiency. But the second one, which is probably more important, is the fact that our baseline Monte Carlo includes only the fully elastic contribution, and we'd like to correct that fact using a dedicated measurement, which is based on the dilepton events, where we basically extract the dissociative scale factor that will also take into account the missing contribution from single dissociative and double dissociative process. So what we are doing, we are taking a gamma-gamma to LL events at higher invariant masses, above 2 times mass of the W, and then after the background subtraction, we just estimate the scale factor, which tends to be pretty large, around 3.6, and this is also the evolution of the scale factor with a dilepton invariant mass. To extract the signal, we are using a simultaneous fit performed to the signal region and 3 control regions. So this control region basically serves us to constrain the inclusive backgrounds. At the end, we observed 307 events in the signal region, where 132 background events are expected. This allows us to establish a first observation of this process at the level of 8.4 sigma. We have also measured the fiducial cross-section, which is at the level of 3.13 femtobarn, and the theory predictions somehow lie on the lower side, and they are between 2.1 and 2.6 femtobarn, depending on the choice of the soft survival model. So these 2 plots on the bottom shows you how where this, first of all, our signal region lies, and then various control regions that are used to constrain the backgrounds. This brings me to the summary. I hope I have demonstrated you that we have a very rich physics program of 2-photon interactions at the LHC. The nice feature of that is the measurements typically are at the boundary of electroweak forward and heavy ion physics, and utilize both PP and LED data sets. And then we have also a diverse set of measurements performed with Atlas This includes the first observation of a new standard model process of gamma-gamma to WW scattering, precision cross-section measurements, non-standard BSM searches, and also the first proton-packed photon collisions observed with a new AFP spectrometer. So to me, this is clearly much more beyond simple QED testing, and it also serves as a very nice groundwork for more detailed studies in the future. Thank you.
Thank you very much for these nice results, Mateusz. I'm sure there are questions. Lucian?
Hi there. Hi, Lucian. Yeah, yeah, really nice talk. Very interesting. I have a couple of questions about slide 14.
Yes.
So first, just so I understand what's going in, you've got the Monte Carlo results, I guess, on those plots. What is producing those? I'm just wondering about that.
So yeah, so these are the pre-fit results. So here we are using Herwig plus
Oh, I got
Elper.
that. Herwig. I see.
Multiplied by this survival factor.
And you take a universal survival factor for the dissociation and the elastic, I guess.
Well, at the end of the day, these are mass-dependent survival factors.
Okay, so a universal mass-dependent survival factor for the dissociation and the elastic. Is that right?
I think we scale those with respect to the super-G predictions at the end of the day.
Ah, well, the Monte Carlo you had will only have dealt with the elastic case because we've only just released the case with the dissociation.
Okay, we had some numbers at the end.
Okay, right. Or maybe we can discuss that offline. Yeah. So, and the other question was about reference 31. So, does that still include this sort of unphysical cut on the impact parameter between the lepton pairs and the protons?
Well, yes, it does, but I wouldn't call it unphysical at the end of the day. Well, it's just you know, I would call it heavy ion specific, maybe.
How do you mean?
Because okay, so the story is a bit more complicated. So the same set of requirements are applied in Starlight. And
well, yeah, I think they're also unphysical in Starlight. That's another question. I think they apply them there because it makes the impact parameter integral easier to do.
Well, I think the justification in terms of heavy ion collisions for that cuts is much simpler. This, to me at least, they take into account the decrease of the effective charge once you go closer and closer to the ion.
Well, I think in the proton case, you're effectively assuming that the lepton pairs can interact strongly with the proton. I mean, that to me is what that corresponds to. So that to me seems, you know, it seems unphysical. But
I think okay. So the primary reason for that cut is the coherence condition, not the chance of strong interaction between the.
Well, in the proton case, I think that's what it effectively corresponds to.
I don't think so. You can also have like gamma star exchanges, things like that.
Sure. You can have of course, you can have QED interactions between the lepton pair and the proton, but those will be at a much lower level. So I mean, but you cut out the whole cross section in that region effectively. That model does. So I mean, to me, I think it's questionable. I think it's whether you can say that's preferred. I'm not sure, but okay. Anyway, thank you.
Okay, it seems Valerie has a comment on this.
No,
if it's not directly.
I've got a question. I've got a question concerning slide 13, please.
Okay. Sorry, Andy.
Yes. So the question is, it's a very strong condition of the Xi differences. What is the resolution of AFP in Xi, please?
I think we can read it directly on this plot. So the resolution of this peak is dominated by the Xi resolution from the AFP side. So
what I thought, yes.
Yeah, I mean it's hard to read this number from this plot, but it's probably around 0.003, something like that.
Yeah, thank you.
Okay, then I think Andrew had a remark on what Lucian was asking about.
Yeah, I just wanted to quickly point out that, I mean, it's very interesting, the topic of soft survival and the theory predictions. One of the things that the paper is trying to do is compare the measurement which is independent of this to various different theory predictions, but we'd welcome feedback from Lucien et al. We can always add more theory predictions, I think, but just to clarify that the measurement itself is independent of these issues around soft survival.
Yeah, that's a fair point. We don't assume any soft survival when doing the fiducial cross-section measurement. So.
Okay, we still have 5 minutes until the coffee break. I still see raised hands by Valerie. Do you still want to comment?
No.
Or are there other questions?
No, I think Lucien said everything.
Okay.
Hi, this is Aram. If I can quickly ask a question on slide 15 for the exclusive WW measurement. You mentioned that the no AFP tag was used for this result, which is quite impressive. But I didn't quite catch what was the reason. There is just there is no suitable data with the tag, or why not?
Well, this is a first reason, probably the primary reason, because here we are utilizing a full run-2 data set. The second reason is that you have the presence of neutrinos, so it would be much harder to correlate, the central detector kinematics with the proton kinematics.
Okay, thanks.
And I guess you would have much less events because you would require for the protons to be in the AFP, so the efficiency is much lower. And we reach 8 sigma, so okay, there might be some potential to have lower efficiencies, but still. Andrew?
Yeah, I mean, in addition to the very high masses, then the efficiency will be high for AFP, but the available data set for AFP is much smaller than the full run-2. So if you look at the plots, it probably says 14.6 inverse femtobarns on the AFP result, and we're using 139 to get the full result. So it really wouldn't make very much difference if we added it in now anyway. That probably isn't true for run-3, right? When you expect to have much more of the full data set available and the time of flight detectors to enable this to reduce backgrounds because of this lack of kinematic matching.
Yeah, let's hope so.
Okay, yeah, this is what I was wondering, if for run-3, if they are on equal footing in terms of integrated luminosity, if one can probably expect some improvements in the measurement. Yeah.
Right, any more questions or comments? And since it's also a general discussion, we could also go back to some of the other things that were presented in this session. All right, I don't see any raised hands. I want to remind people of the fact that we have a specific discussion session on the photon-photon induced processes today at 12:55. I mean, this then can also go a little bit more in detail in the calculations that are compared to the measurements and so on. So that hopefully will be quite interesting. Otherwise, we will close the session for now. We will have a 50 minutes coffee break. Please feel free to continue discussing whilst we're on coffee break, or just go and get some coffee. And see you back in 15 minutes. We'll restart at 11:35 Prague time. Thank you to all the speakers in the session again.
Hi, can people hear me?
Yes.
All right, very good. Okay, welcome to the, let's say, the third part of today's session. Let's get started. And we will cover talks on VBF production of vector bosons, as well as 2 talks on vector boson scattering. And the first speaker is Jun, and presenting us the measurements of vector boson production via weak-boson fusion at Atlas, with Atlas detector. Jun, could you share your slides, please? Ah, great.
Yeah, I can hear. Okay, you can see that, right? Can you
yeah,
hear me?
Yeah, I can
Okay.
see your slides and I can hear you. I think, okay, looks good. Please go ahead.
Okay, so please let me know if there's any connection problem. All right. Okay, thank you. Hi, today I'm going to report the Atlas result on the measurement of the vector boson. Hold on one second. How do I know? Okay, I'm going to present the Atlas results on the measurement of the vector boson production by weak-boson fusion. As we all know, the non-abelian nature of the symmetry gauge groups of the Standard model allows self-interactions of weak boson, like the triple and the quartic gauge boson couplings. The vector boson fusion and vector boson scattering processes are also very important in studying the mechanism of the electroweak symmetry breaking, which has been a hot topic for many years. At Atlas, there are 2 modes to measure the to do the VBF study. One is using the WJJ and the other is the ZJJ. And the latest result is the Atlas ZJJ measurement with the full round-2 data sets. So today I'm going to just report one single result. And this result is done in this result, we did the differential cross-section measurements by using 4 different variables, the PT of the Z boson and the digest mass, rapidity separation of the 2 leading jets, and the signed azimuthal angle between the 2 leading jets. And with these variables, we can probe the kinematic properties of the VBF process. In addition, we can also make constraints on anomalous weak-boson self-interactions. Okay, in this measurement, the signal electroweak ZJJ events is defined by this T-channel exchange of the weak boson, as shown in the top 2 Feynman diagrams, which is extremely sensitive to VBF process, and will require Z to decay leptonically either to EE or mu-mu pair. The full data sets, about 139 inverse random band data, is used, collected from 2015 to 2018. Well, since different generators of the different generator predictions do not agree with each other, so this measurement is made model independent. So people can compare the performances from different generator predictions. Okay, for the simulation, the signal is the electroweak ZJJ process, which is predicted by using 3 different generators, Pahag, Herwig at the next leading order, and the Sherpa at leading order. The dominant background is the strong ZJJ events, which as shown at the bottom 2 Feynman diagrams. And it's also being simulated by 3 different generators, Sherpa, next leading order metagraph, and leading order metagraph. Of course, there are also small contributions from some other small backgrounds like the diboson, TT bar, triboson, and tt+jets predictions. Yeah, so this table shows the details of the generator information. All right. So for the event selection, it is largely based on the topology of the electroweak ZJJ process. So in this process, since we require Z to decay leptonically, so then we require the 2 leptons to have opposite charges in same flavor, and we'll also require the digest system to have invariant mass greater than 1 TeV, and the rapidity separation between the 2 leading jets be greater than 2. In addition, we also require the reconstructed Z boson to be centrally produced relative to the digest system, and also require the Z boson and the digest system to be approximately balanced in transverse momentum. So this bottom table shows the event yields after all the object and event selections for data and different physics processes with the different generator predictions. We can see there's a large spread of the large spread among different generators for both electroweak and strong ZJJ processes. And for electroweak ZJJ processes, the largest difference is coming from the Sherpa sample, which is much less than the other two. And for the strong ZJJ, the largest difference comes from the next in order meta graph. So the first uncertainty of these numbers is from experiment. The second is from theory. So as you can see, for the strong ZJJ events, we have a large theoretical uncertainty. Okay, in addition, we'll also, well, in the following slide, we're also going to show you the, we also see this disagreement in event yields between data and Monte Carlo, and also there's some shape differences. Okay, this bottom left plot shows the digest mass spectrum after all the selection. As you can see, we can see this poor data Monte Carlo agreement. Well, this mismodeling is even more pronounced at the high mass region. Okay, this is using Pahag EWZJJ and Sherpa strong ZJJ. And the bottom right plot shows the predictions from different generators for different physical processes. So the blue curves are for the 3 different strong ZJJ generators, which behave very differently. And also we have we also have different behavior from the electroweak ZJJ generators. Okay, from these 2 plots we can see, okay, the bottom right plot also shows, this mismodeling of the different generators also, really correlates with, what kind of generators you are using for prediction. So from the 2 plots, we can see we cannot simply get the signal by just, subtracting the background prediction from data. So data-driven method is used to constrain both the shape and normalization of the strong ZJJ events to extract the signal, electroweak ZJJ events. Okay, to do that, 4 regions are defined based on 2 important parameters. The first one is called chi-z, as defined here. Here, y means the rapidity. So we take the difference between the rapidity of the dilepton system and the average rapidity of the digest, then divided by the rapidity difference of the 2 jets. Okay, the other variable we are using is called the n-gap jets. That's the number of jets in the rapidity interval between the leading and subleading jet. Okay, based on these 2 parameters, 4 regions can be defined as shown in the bottom right figure. Then the electroweak ZJJ event will be extracted in the signal region as shown in red by using the binned maximum likelihood fit. And this fit is done simultaneously in all 4 regions. This is the definition of the likelihood. Okay, and so for the electroweak ZJJ process, its magnitude is adjusted by the signal strength mu I. And for the strong ZJJ events, their original shape and magnitude is got from the Monte Carlo, but they're adjusted by using this BL or BH parameters. L means low chi-z region, H means high chi-z region. And we also introduce another parameter that is the FXI. This is to provide residual corrections when we do extrapolation from control region A to signal region. Okay, then we can do the fitting using this likelihood. Since 3 different strong ZJJ generators were used, then the fit is done 3 times, for all of them, once for each of them, right? Okay, so we can see before the fit. Okay, that's the left 2 plots. We have, these 2 plots in the left are using 2 different strong ZJJ generators. They all have some kind of mismodeling. in the control region, right? But that means the modeling is different. However, after the fit, so they all get quite nice agreement between data and Monte Carlo in the control regions. All right. Okay, so since there are three fits, then the final electroweak ZJJ signal is taken to be the middle point of the envelope of the three fit results. And these three fit results are also used to estimate the corresponding systematic. Okay, talking about the systematic, I just want to show you some dominant ones. So these four plots show you the fractional uncertainty of some dominant systematics. Okay, for two different variables, MJJ and PGLL. The top two plots are for the inclusive ZJJ cross-section measurements. The bottom two are for the electroweak ZJJ and measurements. So we can see, so the jet systematics is in light blue. So that really dominates the inclusive ZJJ result. And of course, it is also quite pronounced in the electroweak ZJJ process. And the strong ZJJ modeling, which is in dark blue, really dominates the electroweak ZJJ result. Okay, and this is composed of 3 parts: generator, scale, and PDF. And among the 3 of them, generator choice is the largest one. And there's another dominant systematic coming from statistics. Now let's look at the final result, first with the electroweak ZJJ production. As mentioned before, so this differential cross-section was measured as a function of 4 different variables, as shown in the bottom 4 plots. So here we overlay the final data measurement and which is compared with the 3 different electroweak ZJJ generator predictions. Okay, so the Herwig sample, which is in red, okay, this Herwig sample generally prediction agrees reasonably with the data in all the 4 variables. And for the Powell sample, which is in blue, it overestimates in the high digest mass and also high delta Y JJ and intermediate PTLL. And for the Sherpa sample prediction, which is in orange, so generally in all the 4 variables, it underestimates the data. So this is due to some non-optimal setting of cut flow in the generator. Then the fiducial cross-section can be calculated by integrating the digest mass spectrum. That gives the value of 37.4 femtobar with the corresponding statistical and systematic uncertainty. And this value is in nice agreement with Herwig prediction, which is 39.5 with the corresponding uncertainties. Okay, so from this measurement, we can provide some constraints on what kind of theory model to be used for future VVF and VVS measurements. And from these results, we already know Herwig sample performs better. Now let's move on to the inclusive ZJJ production. So we did the same differential cross-section measurements as function of the same 4 variables measured in signal region and control region. So the bottom 3 plots show you the final measurements with the 2 different generator predictions, 2 different strong ZJJ generator predictions, and in both the signal region and also the control region A. And to do this comparison, we also need to choose one electroweak ZJJ generator. From the previous slide, we know Herwig predicts better, than the other 2. So Herwig sample is used here. So from these 3 plots, we can see, in general, the next leading order metagraph generator predicts much better than the Sherpa sample, which is in green. Okay, so these measurements can also be used in the future to reevaluate the electroweak ZJJ process if any new strong ZGG prediction becomes available. All right, in addition to the precision measurements, as just mentioned, we can also test the anomalous weak-boson self-interactions, which can be described by this effective field theory. The Lagrangian is shown here, the standard model part and the anomalous interaction part. The Ci over lambda square is the coupling strength. OI means the dimension 6 operators. Then the cross-section can be calculated and can be split into 3 parts. The pure standard model part, the interference term between standard model and dimension 6 operators, and the pure dimension 6 operators. Then we want to make constraints on dimension 6 operators in Warsaw space, that is, and for both CP even and CP odd. And these plots on the right-hand side show the expected impact from the interference term and the pure dimension 6 operators on the 4 variables we mentioned before, and also in different occasions like the CP even or CP odd. So by just a quick look, we can clearly see this delta phi JJ variable is affected, is so much more sensitive than the other 3 variables. But it is more, but if you look closely, you can see it is more sensitive to this interference terms. And for this PTLL variable, it is also kind of somehow sensitive to this anomalous interaction, but it is more sensitive to the pure dimension 6 terms. So in general, since delta phi JJ is much more sensitive than the other 3, so this variable is used to make constraints on the anomalous interactions. So this bottom table shows the constraints by using this variable on dimension 6 operators, and these constraints are derived by with or without the pure dimension 6 terms. So we can turn on or turn off the pure dimension 6 terms, and we get the constraints, and the constraints generally doesn't affect that, doesn't change it that much. And you can also, I'm sure you notice this at the bottom right corner of this table, you can see very low p-value for this CP odd operator. And this shows very low compatibility, with the standard model prediction for this CP odd operator. Okay, this slide I just want to quickly show you some bonus plots for this FFT interpretation. So the left plot just shows you the, for example, we vary the coupling strength of this CP odd operator, then around the best fitted value. Then correspondingly, in the right-hand side plot, we show the prediction from the interference term and pure dimension 6 operator terms, right? How they change, correspondingly to the variation of this coupling strength, and at the same time in comparison with the data. Okay, this is some bonus plots. You can find more plots in this link. Okay, to summarize, full round 2 Atlas data has been used to measure the cross sections of the ZGG events, to probe the triboson interaction, and also to test the gauge symmetry of the standard model. And differential cross sections are measured for both the electroweak and inclusive ZGG using 4 different kinematic variables, which can test different electroweak ZGG generators with the assumption of no new physics, and also for the future to reevaluate the electroweak ZGG events when new strong ZGG prediction becomes available. So in addition, this can also be used to probe some kind of new physics to search for anomalous weak-boson self-interactions, and it shows that the delta phi JG in the variable is very sensitive to this interference term between the standard model and dimension 6 operators. Okay, that's all for my talk. Thank you.
Okay, thank you very much for these detailed slides and also for being on time. Are there any questions, comments?
Hi, I'm Marco Zarro.
Hello.
Can I ask a couple of questions on the Monte Carlos that you're using?
Yes.
So my understanding is that for the strong production, the only one which is NLO accurate is NG5A Einstein NLO. Is that correct? So Sherpa is leading order accurate in this case.
Yeah, Sherpa is leading order. Yeah.
Okay. So it comes to no surprise that an next to leading order accurate tool shows a better agreement. But why did you mention that you're expecting for other strong Monte Carlos you are waiting for having other stronger simulations to re-extract the Electroweak sample, or maybe that's just my misunderstanding, but it was in your conclusion, for example.
Well, this is yeah. So I think this is a general strategy, right? So you always you get constrained. There's no certain preference, where which generator will perform better or not. You have to rely on the experiments to determine which performs better, right?
Yes, but an next to leading order accurate one, I mean, regardless if it's Malgraph or Sherpa or PowerEgg, whatever, I mean, it has it's supposed. I agree that until you put the data on top of the predictions, you don't know, but it's in principle supposed to be better, no?
Sorry, can I interrupt you?
Sure,
yes.
Go ahead.
I'm Takuya. Atlas uses the Sherpa with the next to leading order prediction up to 4 partons, actually. It's an NLO.
But is the one quoted here? Because I'm surprised that it agrees with, in terms of events, with the leading
sorry,
order.
right. I guess I made a mistake. It is the next leading order. Yeah, for Sherpa is the next leading order. Sorry, I misspoken just now. Right. For Sherpa is the next leading order for the strong ZJG events, and the leading order is for Metagraph 5. The second, so this one. So the for Sherpa and the is leading order MG5 plus PY8. This is a leading order, and MG5 at next leading order. Of course, this is leading order. Yeah, so Sherpa is the leading order. Next leading order. Sorry, I misspoke just now.
Kenneth, you have your raised hand up.
Yeah, can you hear me?
Yeah.
Yeah.
So my question is a bit on the same lines, which is, I mean, you have, if you know the data disfavor some of the ZJJ QCD predictions, then why do they enter into the uncertainty?
I'm sorry, there's a bad connection. Could you repeat?
Yeah, sure. If you know that the data disfavor some of the background predictions in some sort of control region, then why do they enter into the uncertainties?
Well, I think this is again, so I think let me see. You mean yes? I think well, so okay, let's put it this way. So different generators, they all kind of like as we see, for example, from some control regions, they all perform badly, right? Of course, the extent, how badly they, some propose even more badly than the other. So, but I think we don't want just based on these to be very selective and to prefer any specific generators. So we want, I think it will be a safe way to include them all, in estimating the systematics. Of course, some propose a little better than the other, but I don't think we should just, throw them away, just because of this.
Yeah, sure. Just to make a comment. Yeah, I don't. But it looks like at least the ICHEP and the low predictions is not that bad in terms of describing the data. But I saw Bogdan had his hands up, but it's not. Yeah.
Yeah, it is not that bad. This in a math graph compared to Sherpa. Yeah.
Okay, so just to say one quick thing, because we do have to move on soon. I think we can come back to this discussion for the general discussion later today. In addition to that, we were planning to have a dedicated discussion session on Friday, tomorrow at the end of the session, precisely dedicated to this kind of discussions. So I encourage people to join the discussion on Friday. But before moving, I think Marco had his hands up. We can just have this last comment and then move to the next talk. Marco, did you want to say something?
Yes, well, about this thing that was said. I mean, for example, are you including, given that Sherpa had this problem with the color flows in the Electroweak prediction, are you including its prediction among the uncertainty? So are you evaluating the uncertainty, including the fact that it predicts, you have one generator that predicts half of the yield of the others?
Yeah.
But, I mean, this blows the uncertainty artificially, I would say.
Yes, and okay. So in the end, you're gonna have to fit, right? So so in the end, you tried with, of course, by looking at these raw numbers, of course, you have a large difference between different generators. But in the end, we do the fit, right? So this kind of large difference cannot be, washed away, by the fitting. Of course, I guess what really it is left is somehow, the shape differences, right? So this fitting really helps a lot.
I think what's important to notice here is really that this strong component is evaluated in a data-driven way and on the bin basis in order to avoid a bias of the electroweak shape afterwards.
Yeah, exactly.
This suppresses the effects. Yes.
Okay, I think sorry, go ahead. No, I was just going to say we really have to move on, but as I said, let's come back to this during the discussion session. Unless you can finish your thought, Jun, and we can move on.
Sure. One second.
All right. Thanks a lot for your talk. Now we go to Sandeep, who will tell us about recent results for vector-boson scattering from the CMS experiment. Please go ahead.
Okay. Hello, everyone. So I'm Kaur Sandeep from Punjab University, India, and I'm glad to be here to present the recent results on vector-boson scattering from CMS. So given below are the various analyses that I will be discussing in next 15 to 20 minutes. Coming to slide 2, let me give a brief introduction and motivation behind my talk. So as we all know that the observation of the Higgs boson, it's consistent with the standard model within the current uncertainties, and also the W and Z gauge bosons, they acquire the longitudinal polarization via the Higgs mechanism. Basically the 3 Goldstone bosons, they are eaten up by the W and Z. But the question arises that is the Higgs boson lone player responsible for the electroweak symmetry breaking? So that is why we have the measurements of the vector boson scattering processes, as they are the key process to experimentally probe the nature of electroweak symmetry breaking. And the Large Hadron Collider, it makes it possible to measure the many on this slide, slide 3, there is an overview of the VBS measurement. So talking about the VBS topology, let's have a look at the illustration on right-hand side. So basically, we expect the two energetic forward jets in opposite hemisphere with the large dijet mass and large rapidity separation. And in the experimental analysis, what we do is we select diboson events with the VBS-like jets, and then we estimate the non-VV backgrounds. Basically, we have two kinds of backgrounds here. First one will be the non-prompt or the reducible one that is selected due to the misidentification, and its estimation is done from the data-driven techniques. And then we have the prompt background that is selected without the misidentification, and its estimation is from the Monte Carlo. Then doing these background estimations and taking into consideration the various uncertainties, we can perform the various measurements like the inclusive and the differential cross-section measurements, as well as we can perform the search for the anomalous gauge couplings. Okay, with this, I come to the very first analysis, that is the like sign WW and WZ VBS, in which full run-to data is exploited. So this is the first simultaneous same sign WWJJ and WZJJ analysis with the fully leptonic final state. And we can have a look at the one of the Feynman diagrams corresponding to the electroweak prediction, as well as the QCD prediction for both the WW and WZJJ processes. So for the like sign WWJJ process, electroweak prediction, it is dominant over the QCD induced, and we have the distinct same sign lepton state with the low background. Talking about the WZJJ process, so it is a background in the like sign WWJJ process, but it's interesting on its own as well, as it has the sensitive to the charged resonances. And of course, it has the clean signature, but the background is higher as compared to the like sign WW. Then on next slide, we will talk about the event selection and the background estimation. So we can have a look at the table on the left-hand side. So these are the basic lepton selections and the VBS selections that are done in the WW signal region and the WZ signal region. So these kinematic selections are good enough for the WW signal region in order to separate the electroweak and the QCD background, but WZ signal region is still dominated by the QCD WZ events. So the multivariate analysis for WZ is carried out in order to enhance the WZ electroweak production with respect to the large WZ QCD production. Talking about the background estimation, so on the table at the bottom right, we have the various categories and their estimation. So the major background in the WWJJ process is the non-prompt, and it's estimated from the data-driven technique. Then we have the wrong sign background, which is estimated from the charge mis-ID scale factors and the simulated opposite sign events. And of course, we have the triple charge requirement also there, which reduces the wrong sign background by a factor of approximately 20. Then we have listed the other backgrounds which are estimated from the simulation. Please note that the backgrounds that are marked here with the star, they have the normalization assessed from data, and the others, they are normalized to the best theoretical cross-section. Okay, then on the next slide, we have the analysis strategy. So basically, the statistical analysis, it's done by simultaneously fitting the signal yields in the WW and WZ signal regions, as well as the background yields in the control regions, basically to assess the normalization from the data. We can have a look at the dijet mass distribution and the dilepton mass distribution in the WW signal region, and then we have the BDT distribution in the WZ signal region. So these are the distributions that are included in the fit, and we can see good data MC agreement here, and also the separation between the electroweak and the QCD background is good. Then from the yields table below, we can see that the post-fit yields, they are agreeing quite well with the observed values within the uncertainties. Please note that this analysis is right now statistically dominated, so that's why the statistical uncertainty is higher as compared to the systematical uncertainties. Coming to the results section, so in results, we have the inclusive fiducial cross-section measurements. We have the theoretical predictions with and without the NLO corrections, and we can see that the measurements agree quite well with the predictions here. Coming to the significance, so for the electroweak WZ, we have the 6.8 sigma observed, slightly larger than the expected one, that is 5.3 standard deviations. And for the electroweak WW, the significance is far above 5 standard deviations. So apart from the inclusive fiducial cross-section measurements, we have also the absolute and the normalized WW electroweak plus QCD differential cross-section measurements on various distributions. And similarly, we have the WZ electroweak plus QCD differential cross-section measurements on the dijet mass. And we can have a look at the dijet mass distributions both for WW and WZ. And we can see here that the measurements, they agree well with the predictions with and without NLO corrections. And at this point, we are not sensitive enough to say that to which one the measurements agree more. Okay, so with this, we come to the next analysis, that is the polarized same sign WW-VBS analysis done on the full run 2 data. So that's the first analysis of its kind with the real data. It's the one of the high profile analysis for the high luminosity LHC, and it's possible to do it right now. So basically the signal here is the purely longitudinal component, then we have the purely transverse component, and then we have the partially longitudinal component. Talking about the event selection and the background estimation, so it's the same as the unpolarized WW-VBS analysis that I just discussed before. Here we have the 2 sets of results that are based on the frames of defining the helicity eigenstate. So the first one will be the WW center of mass frame, and then we have the initial state pattern frame. And we have used the multivariate analysis here. We have the 2 signal BDTs to measure the various components, and we have the inclusive BDT here to separate the electroweak component from the standard model background. In the analysis strategy, so we will be, we have the simultaneous fitting of the WW signal region, which have the bins in the inclusive BDT and the corresponding signal BDT. And we have the remaining control regions also simultaneously fitted, same as what was done for the unpolarized WW-VBS analysis. Coming to the distributions on slide 9. So these are the corresponding BDT distributions for the inclusive BDT on the left hand side, and then we have the distribution corresponding to the longitudinal, purely longitudinal component of WW, and then we have the partially longitudinal. And we can see the good data MC agreement here. And also I would like to mention that the binning is chosen here in such a way that the signal is flat in the distributions. And we can also have a look at the expected yields in the longitudinal component analysis, and the background agrees with the total background agrees with the measurements quite well here under the uncertainties. This particular analysis is also statistically dominated at this point. So we can see that the statistical uncertainty is quite high as compared to the total systematic uncertainty. Okay, with this, we come to the result section here. So for this polarized same sign WW analysis, we have the fiducial cross-section measurements in both of the frames, and we can see that the measurements, they are agreeing nicely with the theoretical predictions under the uncertainties. And we can have a look at the log likelihood plot as a function of the longitudinal WW cross section on right hand side, and we can see that the observed upper limit is 1.17 femtobarn inverse as compared to the expected. It's around 0.88 femtobarn inverse, and we have also quoted the observed and the expected significance for the partially longitudinal component, and similar set of results are there for the initial state pattern frame. Okay, with this we come to the next analysis, that is the ZZ vector boson scattering. In this also the full run-to data is exploited. So this is the basically the measurement of the electroweak ZZ production using the 4 lepton events, and it's really clean and the fully reconstructible final state production, and with very small instrumental background. So the background estimation is mentioned here. So the major background will be the QCD ZZ in the reducible backgrounds, and it's estimated from the Monte Carlo. And then we have the reducible backgrounds, which are estimated by the data-driven techniques. So the simple variable approach was not enough here. So that is, as we will be observing it in the distributions on the next slide. So we have made use of the matrix element discriminant here to enhance the electroweak production. And the BDT was also studied here, and it gave the consistent results. So we have defined the 3 regions here to measure the electroweak production. So first one is the ZZJJ inclusive region, then we have the VBS enriched loose, and then we have the VBS enriched tight, and we can have a look at the various selections, lepton selections and the jet selections in all the 3 regions. Okay, so looking at the distributions in the inclusive ZZJJ region, here we have the distribution for the dilepton mass and the delta eta JJ distribution, and here the electroweak ZZ component is shown as a factor of 30 here, and we can see that we need to use the matrix element discriminant, and we can see here that we have the excess in the data if we exclude the electroweak component here, and we can have the we have the significance of around 4 standard deviations here, slightly larger than the expected, that is 3.5. And then we have also the cross-section measurements that are electroweak and the electroweak plus QCD in all the 3 regions, and we can see that the measurements, they are agreeing nicely with the theoretical predictions within the uncertainties. Okay, coming to the next analysis, that is the W gamma VBS, in which the 2016 dataset is exploited. So the major background here is the QCD W gamma JJ, which is estimated from the simulation, and then we have the fake photon, fake lepton, and the double fake background, which are estimated from the data-driven technique. Then we have the other backgrounds that are estimated, like diboson, single top, etc., that are estimated from the simulation. Here we can have a look at the low digit mass control region, that is in which we can see that we have the good data MC agreement, and we validated the background estimation methods with the help of this. We can also have a look at the yields in the electroweak signal region, and we can see that the measured observation, it agrees quite well with the prediction here in all the 4 channels, that is the electron barrel, electron end cap, muon barrel, and the muon end cap in this analysis. Then on slide 14, we have the post-fit 2D distributions in the these are the distributions in the diject mass, and the we have the lepton photon mass distributions, and we can see that in all the 4 channels we have the good data MC agreement, and we have also combined the 13 TV results with the 8 TV results here, and significance of the electroweak W gamma is 5.3 standard deviations, slightly higher than the expected, that is 4.8 standard deviation. And this is the first observation of the electroweak W gamma vector boson scattering process. With this, we have also the fiducial cross-section measurements, and which is around 20.4 femtobarn, and it agrees quite well with the theoretical predictions, which is around 17 femtobarn within the uncertainties.
Sorry, Sandeep, just to say you have 3 more minutes.
Okay. Last but not the least, we have also the searches for anomalous couplings. Giving the overview, so basically the traces of the heavy states from the beyond standard model physics, they can be parameterized in terms of the EFT approach. So in these analyses, the limits on AQGCs, they are set by the EFT approach, and the dimensionate operators that can modify the diboson production through AQGCs, they are considered one at a time. We can have a look at the various distributions. We have the full transverse mass distribution for WW and WZ, and for the we have 4 lepton mass distribution for ZZ, and the W gamma mass distribution for W gamma. And we have the these are the analyses in which the maximum sensitivity is in the last bin, but there is no data access at this point of time. Okay, so coming to the unitarity issue, so it's well known that the EFT amplitudes, they grow with the diboson mass, but this growth is unphysical above a certain scale lambda, and this sets the validity of the limit of the validity of the EFT approach. So above this scale lambda, since the data is consistent with the standard model, so what we do is we replace the prediction of the EFT amplitudes with the standard model in that region, and in this way, this leads to the conservative bounds on the EFT Wilson coefficients. So this technique is known as the clipping, and the implementation of the clipping in CMS results is done for the first time here, and it basically means that we are using the EFT only in the region where it is the valid. So the limits on the WW and WZ AQGCs, they are reported in this way also for the first time. And on next slide, we can have a look at the results. Here we have the results for WW and WZ without considering the unitarity bounds, as well as with considering the unitarity bounds, and we can see that the limits are derived by the WJJ production process. Then we have the limits from the ZZ and the W gamma, and the unitarity bounds are also mentioned here. And with this, we come to the summary slide. So the latest CMS results on the electroweak scattering of WW, WZ, ZZ, and W gamma are presented. We have the inclusive cross-section measurements here. Then we have the first measurement of the polarized WW electroweak cross-sections. And we have also the first differential cross-section measurements of like sign WWJJ and WZJJ processes on several distributions. And then the limits on dimensionate Wilson coefficients, they are set for the anomalous quartic gauge couplings within the EFT validity for the first time. Okay, thanks so much.
Thank you very much, Sandeep, for this nice summary of the results. Do we have questions, comments? Please raise your hands. Thomas, go ahead.
Hi, Thomas here. Can you say a little bit more about this clipping in order to save unitarity? And does anyone know how this approach compares to these unitarization attempts of Zeppenfeld and company?
Okay, so basically this clipping method is, as we know, that the EFT amplitudes, they kind of grow with the diboson masses. And we know that this growth is unphysical above a certain scale lambda. So, and this scale, it is derived from the partial wave unitarity condition. And of course, they are, this scale is also the function of the Wilson coefficient. So what we basically do is, above the scale lambda, for the AQGC simulation, the events that will be violating the unitarity, events violating unitarity means in which the diboson mass, it will be exceeding this scale, particular scale lambda, they will be rejected. And the data and standard model processes, they are not affected in this particular process. So in this way, this gives us the conservative bounds on the EFT Wilson coefficient. So we have the two set of results here. In the first one, in which we do not consider the unitarity, and in the second one for the WW and WZ, we have considered this unitarity constraint, and we have rejected the events that violated unitarity. And of course, this number of events that violate the unitarity, they vary with the operator values because the scale, it depends on the operator values.
Okay, thank you.
Joanne, please go ahead.
Yes, I have one question regarding the polarization analysis for the same sign WW. So you are training two PDTs here and you are doing a 2D fit. So the normal one, the inclusive one for the separating the same sign, and then you have another training, two other trainings for the extracting the longitudinal fraction and the other fraction. Which variables are you including there?
Okay, so these are there in the backup. Let me go there. Okay, so for the inclusive, for the signal BDTs, these are the corresponding list of the variables that we are using, like the difference in the azimuthal angle between the leading and the trailing jets. And we also have the RPT variable, that is the ratio of the scalar PT products from the leptons and the jets. Then we have the transverse WW dijet mass. So basically the variables related to the jets and the leptons, and the variables related to the correlated between the jets and the leptons. And then for the inclusive BDT, these are the listed variables which we have trained.
So there is some overlap among the variables that you use for both in some cases, like the PT of the jets. They are appearing in both BDTs.
Yes.
And they are trained independently.
Yes.
Okay. And also another question here in the, if I might, on the simulation. Which simulation are you using for the longitudinal and transverse Monte Carlo?
So these signal samples, they are generated with the latest version of MATGRAPH, that is 3.7.2. So it allows, yes.
Okay. Okay, good. And have you estimated somehow like the interference among the different polarization states? Is this possible with the new MATGRAPH?
Yes, we generated the separate, we estimated the effect of the interference.
Okay, and somehow an uncertainty on the templates.
Yes.
Yeah, just to quickly say, it's while it is not quite as let's say technically possible to get to the final state to generate let's say different interference samples between the different polarization states and QCD and the let's say longitudinal contribution. We did some estimations, let's say considering only on-shell Ws, and we pretty much saw that the relative contribution of the interference goes as the fraction of the individual polarization state. So we did take this into account into the fit, but this is a quite small effect. Yeah.
Okay, good. Thanks.
I think we have time for one more question, if there is one. Otherwise, we can move on. Okay, I don't see any other hands raised. Again, thank you very much, Sandeep. You can start sharing the slides. Now we move on to Takuya, who will tell us about the observations of the weak-boson scattering with the Atlas detector.
Hi, can you hear me?
Yeah, we can hear you.
And do you see my screen?
Yes, and we can see your slides.
Okay, so I will present the observations of the weak-boson scattering with the Atlas detector. So, yes, we already discussed the vector-boson scattering. So BBS is one of the most important physics processes at the LHC, not only to test the standard model, but also to test the new physics contribution like anomalous chaotic gauge coupling, AGC. So the experimental signatures are existence of two high tt+jets in forward-backward directions, which leads to high dijet mass in the event, like 400 GeV or 500 GeV or something like that, and two WZ or gamma bosons in the central rapidity, reconstructed in both leptonic and hadronic final state modes. In terms of the standard model test, the longitudinally polarized double boson scattering cross-section is expected to be divergent if we only consider the T-channel or S-channel exchange of the Z-gamma boson, as shown by the orange box. And the term proportional to the energy power to 4 is cancelled by the contact interaction diagram shown by blue box. And the quadratic divergence term is still remained, as shown by the green distribution. In the standard model, this term is also cancelled by the exchange of the Higgs boson, which have the opposite sign amplitude. But in the other word, if the Higgs to WW coupling is slightly different from the standard model, we can expect an interesting structure at the TeV energy scale of this measurement. Also, if there is a new physics at the very high energy scale to where the LHC cannot directly access to, it can also affect the TeV scale distribution. The similar discussion can be made not only for the WW scattering, but also for the WZ and ZZ scattering. So it is important to cover the possible BBS processes comprehensively. And for the completeness of the AQGC new physics interpretation, so Z-gamma scattering is also, W-gamma is also important. And as you can imagine from the left-hand distribution, in terms of the new physics interpretation, so older 10% rough measurement at the TeV scale can give equivalent information as the precision measurement at the electromagnetic scale. It's important to cover the wider and wider mass ranges as much as possible. So to cope with that, so Atlas employed many final state modes in the analysis program. So generally speaking, so if we require the leptonic final states, we can suppress the standard model background, and it leads to the precision measurement in the future analysis. But the number of signals are also decreased, so it is difficult to reach to the higher mass region. On the other hand, if we require the hadronic final state mode, so we can get much more signals, but the analysis will suffer from the huge amount of the standard model background. So based on the final states, we have the 5 different analyses, namely same sign WW, ZZ to 4 lepton to L2 new combination, WZ to 3 L1 new, Z gamma to LL gamma, and semi-leptonic modes, which is the combination of the WW, WZ, and ZZ scattering in the 1 lepton, 2 lepton, and 0 lepton channels. So each channel has, of course, merit and demerit. So it's important to combine all the results at the end of the analysis to claim something to the new physics. Anyway, so Atlas adopts the 2-step strategy for now. So in the first step, we aim for the observation of the standard model BBS processes in 5 sigma accuracy. And then we can extend the analysis to the cross-section precision measurements and the high mass searches depending on the channel. So today, I will mainly show the first step result. So some analysis observed the standard model BBS processes in 5 sigma accuracy. So first, I'd like to discuss about the same sign WW analysis. So based on the 36 inverse fan dataset collected during the 2015 and 16. In this analysis, in addition to the 2 forward jets, we required 2 same sign isolated leptons and large missing ET. So after the event selection, we can already achieve the very high purity signal region, as you can see in the right-hand plot. So this yellow histogram shows the signal contribution. So the signal yields are extracted by the fit to this dijet mass distribution. And we observed the electroweak same sign WWJJ process in 6.5 sigma standard deviation from the background only hypothesis. So we also measured the signal yields as a function of the dilepton mass, which is related to the effective center mass energy of the diboson system. And as you can see in the left-hand plot, so the observed data agree very well with the standard model prediction. But with this statistics, actually, it is not so sensitive to the new physics contribution yet. So right-hand plot, so blue line shows the standard model prediction, and red line is the one with the Higgs to WW coupling set to 0. So even if we assume such an extreme scenario, the difference between red and blue lines are not so large compared to the theoretical uncertainty shown by the shaded area. So for the future precision measurement, we need to understand the signal modeling more to reduce this theoretical uncertainty. We also compare the result with the different Monte Carlo predictions, so Sherpa leading order and POHEC plus PCR next to leading order. So fiducial cross-section in data agreed very well with the next reading order prediction by POHEC plus PCR. So dominant uncertainty, dominant source of the theoretical uncertainties are different between two predictions. So while the choice of the QCD scale is a dominant for the leading order Sherpa prediction, so it is subdominant for the next reading order POHEC, and instead PDF and parton shower uncertainties are dominant. On the other hand, so data accuracy is limited by the statistical uncertainty still. All right, next analysis is about ZZ2 for lepton and 2L2 new combination. So it is a relatively recent analysis based on the Fururan2 dataset corresponding to 139 inverse M1 integrated luminosity. So in this analysis, in addition to the two Howard jets with a high dijet mass, we required two opposite sign same flavor lepton pairs or one opposite sign same flavor lepton pair plus large missing ET significance. So in the full lepton channel, so we can fully reconstruct the boson mass, which is the effective center mass energy of the boson scattering system, as you can see in the right-hand plot. But yeah, it does not lead to the TeV energy scale yet with these statistics. And different from the same sign WW case, so the signal purity is not so great. So there is a large contribution from the irreducible QCD-induced ZZ production background. So in order to enhance the signals more, so we performed the multivariate analysis based on the BDT using the kinematic variables of the Howard jet and the reconstructed Z-boson candidate. So this slide number 10 shows the final discriminant BDT distributions in the full lepton channel on the left and the 2L2 new channel on the right. We extracted the signal used by the fit to these BDT score distribution simultaneously, and we obtained the signal strengths in the full lepton channel to be 1.5 and the one in the 2L2 new channel to be 0.7. A combined signal strength is found to be 1.35 plus minus 0.34, which corresponds to 5.5 sigma observation of the electroweak ZZJJ process. So this is the first observation of the electroweak ZZJJ at the LHC. And next slide shows the beautiful event display to contain the two electrons, two muons, each of which has the lepton mass compatible with the boson mass, and the two Howard jets with the dijet mass to be 2.2 TeV. So for this event, we found for lepton mass, which is the effective center mass energy of the boson system, to be 600 GeV. All right, so let's move on to the next analysis. So tgamma scattering in the two lepton final state modes. It is again based on the 36 inverse M1 dataset. In this analysis, we required one opposite sign same flavor leptons, which have the compatible with the Z-boson mass, so you can see the right-hand plot, and one isolated photon, high PT photon, with a tight identification based on the calorimeter shower shape and so on. And in order to reduce the rare decay of the Z-boson to LL gamma, we require the sum of the dilepton mass and the LL gamma mass greater than 2 times Z-boson mass. So again, so BDT is trained to enhance the signals based on the kinematic variables of the Z-gamma bosons and Howard jets. And I will show some example of the input variables used in the BDT training. So dijet mass and the centrality distributions. In the left-hand plot, you may be aware of that data Monte Carlo disagreement at the highest MJJ region, but it does not affect the BDT score distribution because both signal and background mainly distributes at the lower MJJ region. And right-hand plot shows the centrality distribution. So signal peaks around 0, while the background distributes broadly. And this is the final discriminant BDT score distribution, and the signal yields are extracted by the fit to this distribution. And we found the signal strength to be 1.0 plus minus 0.26 if we use the MATLAB leading order prediction, and 0.87 plus minus 0.23 if we use a Sherpa leading order prediction. So it is a 4.1 sigma measurement of the ttgamma, electroweak ttgamma scattering in the two lepton final state modes. So although two results are consistent between each other within the uncertainty, we found about 10% difference on the fiducial cross-section predictions by the different two generators. So we tried to use the same parameters as much as possible, but there are small differences. For example, so PDF, we use the NNPDF 2.3 leading order for the MATLAB event generation, while NNPDF 3.0 NNLO was used for the Sherpa generation. The MATLAB is interfaced to Fisher-Parton shower algorithm. On the other hand, Sherpa uses the internal Parton shower algorithm. And the choice of the QCD scale is also slightly different. So while MATLAB uses the transverse mass, and Sherpa uses the invariant mass. So maybe these differences can give a hint to improve the signal modeling in the future analysis. All right, let's move on to the next analysis. So BB is semi-leptonic. So it is also based on the 36 inverse lepton dataset. And this is a combination of the WW, WZ, and ZZ scattering in the 0, 1, and 2 lepton channels. So there are two strategies to reconstruct the hadronically decaying WZ to QQ, depending on the target mass ranges. So for the lower mass region, we expect a lower PT-WZ boson in the band, and two quarks from the boson decay can be resolved by the standard tt+jet algorithm. On the other hand, for the high mass region, we can expect the boosted WZ boson in the band, and two quarks from the boson decay are merged together due to the Lorentz boost factor and reconstructed as the one larger jet. So recently, in the past 10 years, Atlas and CMS developed novel techniques to reconstruct such a boosted WZ boson using the larger jet. Sorry. If we reconstruct the jet mass, let's say, using the 4-vector sum of the jet constituents, like a topo cluster, assuming they are massless particle, and mitigate the pileup and soft QCD contribution by some algorithms. So WZ to QQ signal peaks around 80 GB or 90 GB, as you can see in the solid red line in the left-hand plot, while background distributes broadly, shown by the black solid line. So if we define the signal region by applying the mass window cat, so we can estimate the background contribution from the sideband control region data. In addition, we can further enhance the signals by applying the cut on the jet substructure variable, like a D2, as shown by the right-hand plot. So it describes the two-prong likeness inside the jet. And if we apply the upper cut on this, we can enhance the W2QQ signal, shown by the light gray histogram, effectively. So currently, we use the 50% efficiency working point to achieve the background rejection about 50, depending on PT. And in the Atlas, the development of the new boosted boson tagging technique is ongoing using the particle flow-like algorithm or machine learning technique. So in the future analysis, we can expect much better background rejection while keeping the signal efficiency. So it is a key technique to improve the analysis at the highest mass region. So the improvement of the boson tagger can directly improve the vector boson scattering measurement accuracy. Anyway, so this time, yeah, BDT is again trained for the 0, 1, and 2 lepton channels and resolved marginal separately based on numeric variables of the reconstructed bosons and the Howard jets. So this slide shows some example of the BDT score distribution in 0 lepton channel, 1 lepton channel, and 2 lepton channel, respectively. And we extracted the fit, we extracted the signal used by the fit to these distributions simultaneously. So basically, data agree well with the standard model prediction in all of the signal regions. So we found the signal strength in 0 and 2 lepton channel is about 2 times larger than the standard model prediction. On the other hand, so 1 lepton channel was a bit unlucky, and we found the signal strength to be 0.33 plus minus 0.5. And after the combination, we obtained the signal strength to be 1.05 plus minus 0.4. It corresponds to the 2.7 sigma meant of the VVJJ process in the semi-leptonic final state mode, but it can give the strongest limit on the new physics contribution at the TeV scale because it can only access to such a higher energy scale. So for the standard model measurement, as you can see in this table, the systematic uncertainty is already dominant source. But if we only focus on the high mass region, of course, yeah, still statistical uncertainty is the dominant source of the uncertainty. Okay. So I presented the Atlas measurement of the electroweak VVJJ processes as a test of the standard model and the new physics searches. And both precision measurement and the search for excess at TeV scale are important. So to cope with that, we employed many analysis channels to adopt a two-step strategy. So in the first step, we aimed for the observation of the standard model VVS process, and then we will extend the analysis to the precision measurement and new physics search. So today, I presented several analyses to show the 5 sigma accuracy for the same sign WW, ZZ2 for lepton, and WZ23L in the backup slide actually. And we observed we measured the Z-gamma scattering in a 4 sigma accuracy. For these analyses, the statistical uncertainty is still dominant. And for the future precision measurement, it is important to improve the signal modeling uncertainty. So we reported some differences between leading order and next leading order and generators, different generators. On the other hand, I also reported the 2.7 sigma measurement of the VVJJ process in the semi-leptonic final state mode. So towards the high mass search analysis in the future, the key is to improve the boosted boson tagging technique. Okay, so that's all from my side.
Okay, thank you very much for these nice slides. Are there questions, comments? Please raise your hands. Maybe I'll ask one quick question on slide 14. I think for the Z-gamma measurement, when you were showing when you show the 2 mu values, one with Sherpa and one with Markov, so if I understood correctly, the difference here is mostly coming from the central value prediction difference between Markov and Sherpa, correct? It seems like the shape differences, let's say, are not playing a leading role here. Is this fair to say that the agreement in terms of shapes for different variables are reasonable between Markov and Sherpa?
So we found a 10% difference on the fiducial cross-section prediction defined by the truth jet and the truth leptons, truth photon. I'm not sure from where this difference coming from. If in the future analysis with much more statistics, if we measure the differential cross-section, maybe we can say something more about it.
Okay, thanks. Marco, go ahead.
Yes, I have a question on the definition of the fiducial cross-section. So how much does it depend, or is it sensitive to the third jet? Because also studying VBF and VBS, we saw that you should use a certain specific recoil scheme in PTIA in order to have a sensible description of the third jet. For example, the global recoil will give you a lot of radiation in the central region for the third jet. So how much is this important in the definition of the fiducial cross-section?
Yeah, actually, to define the fiducial cross-section, we just picked up the leading 2 truth jets and applied a dijet mass greater than 500 GeV or something like that. And we found the reconstruction efficiency to the fiducial volume is about, let's say, I don't remember well, but over 40% or something. So inefficiency is coming from the tag of the forward jet in the reconstruction or the jet energy resolution. So yeah, maybe the mismodeling subjet can affect this, but I'm not sure. I don't have an answer actually.
Okay, so in principle, the third jet does not enter in your.
It is not used, yeah. In particular for the photonic channels.
Yes, and maybe if I can add something to Marco, it's not used neither for the variables that we use to train the BDT. So it's not polluting the BDT training either.
Yeah, for the leptonic channel, we just use the leading two jets. Yeah, right.
Okay. Are there any other questions? Since we are also in the general discussion session, also questions to the other speakers as well. If not, just to say again that tomorrow we, as we said, we plan to have a dedicated discussion on this at 1 p.m. CERN time. Christine posted the details on chat here for the Zoom connection. So yeah, so I wanted to thank again to all speakers for this session. I think we now move to the dedicated discussion planned today for the photon-induced processes. So I'll let maybe Christine to take over here.
Yes, thanks a lot, Aram. Yeah, let's start the discussion. I mean, we could kick off with some observations or controversial observations and some questions, and I'd be happy for you to dismantle my argumentation. But so what we've seen today, and also there was a presentation yesterday, but Mateusz has very nicely summarized the status of the measurements so far. So, and there were also some discussions on the light-by-light scattering in heavy ions yesterday. So what we've seen is that the photon-photon scattering is higher in the measurements than in the predictions, and the same is true if we look at the newly observed gamma-gamma 2WW. But when we look at the dilepton production, the photon-induced dilepton production as measured by the AFP or other measurements done earlier by CMS or Atlas, this is basically quite well in agreement. So of course, one could ask the question whether this is the sign of anything or nothing at all. And related questions would be A, do we trust the measurements? And B, do we trust the predictions? And are there any good predictions we can basically just take out of the box? And I assume the answer to both of these questions could be no, but I'd be happy to hear some opinions. Yeah, Marco? Marco, did you want to say something, or do you just have your hand raised from before?
Sorry, I didn't raise. Sorry.
Okay, sorry. Yeah, I mean, I also don't see the photon-photon theorists connected, though. There's Marta. I don't know. How much would you trust? No, Mateusz. Mateusz, you would like to comment?
Yes, maybe one point from the experimental side is that, I mean, at least to partly answer the question whether we can trust our measurement is to have alternative measurements from CMS, which are still waiting for both for the full run 2 data set measurement of light by light and WW scattering.
Yeah, that is correct. I don't know whether anyone from CMS is connected that could comment on ongoing efforts on this side from CMS. then maybe would be nice to get some theory perspective on sort of how much do you trust the predictions that the atlas is comparing to.
I raised my hand. Maybe I can say something.
Yes, sorry. I don't necessarily always see people raising their hands. I don't know what's wrong with my
No
Zoom.
worries, no worries. Well, I don't know, in terms of trusting the theory. So for the, obviously there's different measurements you've mentioned there, but for the light by light in heavy ions, I mean, the theory is fairly straightforward. I mean, it's just gamma gamma to gamma gamma from the standard model, and you know, some smallish correction from the fact that the ions can interact. You know, that's the prediction. You compare against our Monte Carlo on slide 9 of Mateusz's talk, but I think in the past you've compared against other implementations, and the results are fairly consistent. You know, if it's some sort of global effect because of the ions dissociating or whatever, I'm not sure I would understand it being mass dependent, for example. So that's one question. So yeah, I mean, I think that the theory is what it is, and is, I would say, reliable. Yeah.
So still, as we've seen yesterday, there were these discrepancies between the prediction in the heavy ions versus the measurement, and now we see basically the same for the gamma gamma to WW.
Yes. Well, I don't know what. So the gamma gamma to WW you compare against Pythia, right? Or what do you compare against?
So that was
Madgraph plus Pythia. Sorry.
Yes.
So again, that's, you know, that's going to be a very well, actually, I mean, that's a question. You say depending on the choice of soft survival model. So I'm not sure what that means, what you've actually done with that, what has been done with that. So that's a question, actually. Excluding the survival model, the prediction is very well understood. Yeah, maybe better to understand that range, what that range corresponds to, actually. That would be a question. You go from 2.1 to 2.6, depending on the choice of soft survival model. Maybe someone can comment.
Yeah, I'm told Andrew has raised a hand and maybe he wants to comment or can answer this.
I have a question related to soft survival to the theorists, but not. I don't want to answer that question. I thought maybe that should go to the team.
Okay, then Mateusz maybe can answer. Otherwise, I'm sure there's someone from the analysis team connected who would be able to answer, but let's go with the speaker first.
Yeah, so the difference in the range is that we are using the same set of soft survival models as for the dilepton production of the AFP. So that's the primary reason, but we did one extra step. So when we compare to our measurements with the fully exclusive prediction that is scaled using a data-driven method, we do end up with the same data to prediction disagreement.
Say that last bit again. So,
well, you remember we also extract this dissociative scale factor directly from the data.
Yes.
So if we apply it to the case of a WW exclusive signal, we still get a lower predicted value comparing to the measurement.
Okay.
It's like a 2.6 femtobarn versus 3.1 femtobarn.
But broadly, what you're saying is that actually the model that you're claiming or you saying, well, describes the lepton data better, describes the W data worse. I mean, these are large errors, I guess, but you know, that's the trend, right?
Yeah, somehow, yes, but the errors are quite large.
Yeah, sure. I mean,
cases.
whether you can say the WW is above anything at this point is maybe tricky, but yeah.
So I mean, in principle, this dissociative scale factor should, you know, also cover the, you know, different admixture of, you know, dissociative to exclusive processes, but also a soft survival factor RD. So all of this should be included once we do this, you know, scaling with this data-driven, you know, factor.
Yeah, and I mean, I guess maybe just to add, it should also cover scale uncertainties, which were, I think, found to be rather large in that conference note, coming from the factorization scales, which was quite interesting.
For which for the gamma gamma?
Gamma gamma to WW from the factorization scale.
Okay, I'm not sure I understand why that would come from, actually. For the theory prediction, it's elastic, and there's no factorization scale. There shouldn't be.
That is when we take the prediction using MatGraph, right, where you have a semi-dissociative prediction as well. And then you can get next to leading order effects where you would have a quark radiating off.
Okay, so for the dissociation.
Yes. But maybe that's also something to be discussed in more detail. But Andrew had a question, so maybe we go with him first.
Yeah, I'm wondering what the prospects are for improving this soft survival calculations for both the elastic and the single dissociative and the double dissociative. The reason why is that I don't think we're too far away now from wanting to make differential measurements of the gamma gamma to WW. And then when we get there, we see all of these different soft survivals as a function of the photon-photon invariant mass, right? So ultimately, if we have very different theoretical predictions on this, that are kinematic dependence, this is going to have a really big impact on them, whether we want to use the tails of these different distributions in EFT fits. I can imagine, I can imagine that being limiting, right, in our sensitivity to new physics in the tails of the distributions, is the knowledge of the soft survival. So how do we improve this? How do we get this down to a much smaller uncertainty between different predictions?
Well, in terms of improvement, we had a paper out a couple of days ago, which hopefully is a step in the right direction. So that does dissociation and elastic with survival factors, which depend on whether it's elastic or dissociative and depend on kinematics, the mass, as you say. That's all within there. Of course, it's a second question when you're comparing to the dilepton data, and we seem to be too high. So that is a separate issue. But of course, having the data, unfolded in terms of distributions and being able to really compare against it and see where exactly that discrepancy is lying would help in that respect. I think that makes sense.
Mateusz?
Just to follow up on that, Lucian, you're just asking, you're essentially suggesting there that we need a lot more dilepton measurements, differential, right, to feed into the soft survival comparisons. Is that right?
Well, I mean, yeah, I mean, frankly speaking, it's difficult to understand how you can get such a low value with what I would consider to be a reasonable model, but that's a separate issue. But certainly having distributions to compare against and see where this is happening would be useful. Yeah, I mean, I think that yeah, I would agree with what you're saying. Yeah.
Mateusz?
Yeah, just to follow up the original question of Andrew, I think from the experimental point of view, it would be very interesting to measure also the ratios differentially if possible. So the ratio of mu to dileptons, basically, just to at least partly get rid of some sort of these effects.
Yeah, I mean, for example, the difference between what you referenced 30 us and you referenced 31 should be essentially, of course, these things depend on kinematics, but to first approximation, universal between those two processes, right? I mean, so in a ratio, those things will largely cancel out, not entirely, but yeah.
I mean, maybe one question concerning interesting distributions to look at. I mean, Mateusz has shown this procedure to extract the scaling factor for the dileptons that is then used and applied to the WW, right? And this is completely data-driven in sort of the dominant Julian subtraction, right? Would it be interesting to study this specific scaling, let's say, as a function of the eta acceptance, or the upper eta cut you put on the leptons or something? Because I think that one, because there's not so much, I guess that one could be studied a bit more in detail or easily, differentially. So sort of the eta of the dilepton system, or just the eta or the delta eta of the leptons.
Yeah, I think so. I think so we have a Monte Carlo that predicts all of these things. So to see, as I say, how it compares in the different kinematic regions and if it's doing a good job is surely a first step. I mean, we don't have WW at the moment, but that's on the way. And then I could say more about that, but yeah.
I mean, then talking about differential distributions, are there any, okay, for the WW there's none, but are there any for the dileptons or the light by light scattering that would be interesting to look at, but have somehow been overlooked? I mean, I guess this also goes out to the people that calculate the light by light numbers.
No, I think the ecoplanarity is very instructive because it tells you can go to different regions where the dissociation is more dominant and the elastic is more dominant, and see how you're doing. But of course, you already present that.
Now you mentioned that the gamma gamma WW is on its way. Do you have a time estimate?
Yeah, order months. The process is just a bit more complicated for various reasons. So it's not just a case of taking what we've got and sticking in the new process. It's a bit more subtle. So made some good progress, but it's not about to appear next week. But you know, I'm actively working on it with students, so it's on its way.
That sounds good then. Atlas has given you something to look forward to.
Yes, and a measurement to compare against as well, which is very nice.
Yeah, exactly. I mean, I guess this is what you want to do if you're not a, let's say, string theorist or so.
Well.
Yeah, I don't know. Any other questions or discussion points that people would like to bring up? Still, it would be very interesting to see these results followed up by CMS, just to make some advertisements to all the CMS people in the room. Go and measure. Maybe one question concerning the AFP prospect. So we've seen now we can measure the dileptons with the AFP, but do we have any estimate of how much luminosity we will take with the run 3?
What do you mean by that, Kristen? You mean specifically to AFP?
Yes, exactly. I mean, just to get an idea how the AFP results that we've had so far will scale.
Enormously. So I would have thought that at least an order of magnitude more than what we have now.
So that would give a lot of lever arm to do much more precise measurements.
Yeah, it's because we took the viable data we took, learning how to use a new detector is quite small compared to the overall run 2, but it'll be much higher compared to the overall run 3 in the end, right? So that means that run 3 is going to have more than run 2, but we'll have a much higher fraction of it. So it should be very high.
Yeah, so these are very exciting prospects. And I mean, I guess, so there's also several parallel sessions that cover some of the AFP capabilities and yeah, explaining the detector and I guess also some prospects will be measured there or mentioned there. That's of course a little bit different from the physics. I mean, maybe coming back to this scale discussion. So that was also very surprising. No, this goes to Lucian, that the scale uncertainty is so high, but that really only comes from the factorization scale. And some people that we discussed with, or that Atlas discussed with, basically put it down. Let me double check. Put it down to sort of all the dissociative effects, where then in higher orders you have quite a big so if you go from leading order to next to leading order and you look at the factorization scale, you can have quite some effects from the quark radiation, so photon radiation of quark lines. That was my understanding, and that was Electroweak. So people that mainly work on Electroweak corrections to diboson processes, and for them, so 10-20% scale uncertainties on a leading order process didn't seem super outrageous. But to be fair, we didn't have the time to do very detailed investigations.
Did you say photon radiation from the quark line?
That was my understanding, but I'm also that was the understanding.
Mm.
Yeah.
Yeah, I think I suspect for the, I'd have to look, but I suspect for the implementation, for the dissociation, you use a photon PDF or something. Is that what you do?
Yes.
Yeah. Okay. And do you use so you use a collinear result with LUXE QED or something, I suppose, right?
That is a bit difficult. So at the moment, it's still one of the older PDFs, but we give the result, Mateo should correct me if I'm wrong, gives the, so the result gives also the difference from the nominal that was using CT14 QED to the MMHT inelastic. So only the inelastic one.
Yeah.
Because if you use the LUXE QED, you will not get the tracks modeled right. So then you run into troubles with the track modeling, and it will have a huge cross section from the double dissociative. And then it gets tricky with the sort of getting the acceptance right.
Well, yeah, and also the LUXE includes the elastic as well, so that would also be wrong. I mean, because you explicitly, I guess, put that in addition, right?
Yes, that's right, but that's the smaller proportion.
Sure.
In that sense.
Yeah. Okay. Yeah. No, that makes sense. Sorry, go on.
Yeah, sorry. I was going to say, and in that case, if you produce the elastic, so in that setup, if you use the photon PDF, even if you have the elastic production, you will have tracks, because then, so for the technical reasons, then Pythia will still fragment the proton, which is not what you will get, right? So
we spent months trying to get Pythia to do the right thing for our paper, so I know what you mean. Yeah. So you deal with the elastic bit separately, and then just for the photon PDF, you only do the inelastic bit where that should be fine, essentially, right?
Yes.
The MMHT inelastic is based on, is fine. I mean, that's up to date. That's based on the inelastic part of LUXE, so it's precise in that sense. Yeah. So right. So indeed, you'll get a factorization scale variation from that, which is an inherent uncertainty in your prediction, because you're using a photon PDF and collinear factorization. So it's just as you would always get if you have a leading order QCD process, you have a big scale variation. It's just the same thing. So that this would be from not higher order photon radiation, but from higher order gluon radiation and NLO corrections of that sort. The point is that actually you can do better than that. You can actually predict this thing precisely without using a photon PDF explicitly. You just directly calculate in terms of the proton structure functions. So the elastic structure functions, the elastic form factors, and the inelastic ones, F2 and F1. And there is then no factorization scale in there. So you're right to include the scale variation here, because the underlying prediction has that uncertainty associated with it. But yeah, sorry for the plug again, but in our Monte Carlo, we do things a more precise way. So you would then not have that scale variation in it. But I don't think there's anything wrong or unusual that in this case you have it there. If that makes sense.
But does one get particles out from your Monte Carlo or numbers?
Particles. So it's all interfaced to Pythia.
Okay, very good.
Well,
Mateusz?
particles from Pythia.
Yeah, so this is a very interesting to hear. I'm just wondering, okay, because this would possibly, remove the issue with the scale uncertainty, but what about the PDF uncertainty or the structure function uncertainty? Is it
That's
like
very low, very low. I mean, it's percent level. These things are, because it's the structure functions are measured in lepton-proton scattering, and they're just known.
Yeah, but I mean, they don't cover a full phase space, so there should be some extrapolation done here and there.
How do you mean? What?
I mean, some super low X and given Q-square regions. That's
Sure. Yeah, absolutely. A low Q squared and so on. But the uncertainty on that is those uncertainties are there, but they're always quite a lot less than the leading order factorization scale uncertainty, generally speaking, which is very large. So
Okay.
the generally speaking, it depends on X, it depends on Q squared, but the uncertainty you get from the inherent uncertainty in the structure functions, if you like, is order a few percent, and that's all quantified. If you look back at the original LUXE QED papers, for example, they kind of spell that all out. Yeah. But anyway, the point is that in our calculation, we use the same structure functions. So it's the same source of uncertainty. And it's, again, at the percent level.
I mean, to give some numbers to my understanding, the MMHT in elastic gives you something like 5%. And I mean, this is publicly calculable from like the Apfel grid, for example, that gives you roughly 5% uncertainty.
Okay. That's just in the scale variation.
No, this is the PDF uncertainty from the MMHT.
Fair enough.
There's the MMHT, that is the uncertainty. That's the uncertainty on the photon-photon luminosity, roughly at that scale. But that corresponds to whatever you can get out of the Monte Carlo if you apply some acceptance.
Sure, and that's the luminosity, so that's squaring up the few percent I was talking about as well. So that seems consistent.
Yes, yeah.
Whereas I guess your scale variation is a lot larger than that. Maybe not. But
yeah, 20%.
Okay, larger, but yeah.
Yeah, and so just as a comparison, so you do have a 10% factorization scale dependence at leading order for the QQ induced IW. So it's not, so that is also a bit consistent. And this is why the electroweak theorists that were looking at this were saying, oh, it doesn't seem completely
no, that's
completely
right.
off. But
yeah, no, it's a QCD higher order uncertainty, and if you're just doing the leading order, yeah, it's the same thing. Yeah. But
if we're talking about scales, what would be the scale that you would use for this process? Fixed scale, dynamic scale? Because that for diboson processes, that is quite that's always a discussion point, and that makes quite a few percent. I mean, okay, that you can already see from the scale uncertainty at leading order, right?
Well, yeah, I mean, as I say, I think from the point of view of our calculation, which uses the structure function approach directly rather than PDFs. So by structure function approach, I mean the same thing you do when you do vector-boson scattering, but with a photon rather than a W or a Z. There is no factorization scale in there. There's just a direct relationship between this cross section and the lepton-proton scattering cross section, if you like. So there just is no factorization scale because there's no PDF. Of course, if you're using a photon PDF, then I think it's just the same rules apply. You would just use, in this case, the invariant mass of the system, but something of that sort. which I guess you're doing.
Yeah. Yeah, that's being done. Any other questions from someone else? Though I guess we are nearing the time that the poster session starts, so they should start in well, in just a moment, 5 minutes or so. So that was also why we put the end of this discussion session around now. I hope there is no, let's say, leftover questions. So that's your last chance to ask. And otherwise, we will close the session for now. Thanks a lot, everyone. I hope you enjoyed the discussion and also the talks. Thanks to all the speakers again. And hope you connect tomorrow as well. Thanks a lot. Bye.
Thank you.
Bye-bye.
Bye.
Bye, everyone.